course, seen in B to K J psi pi pi, and then confirmed in a whole swathe of other decay modes from J psi pi 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 0, DD star, and so on. Today, we take two approaches, both reconstructing X to J psi pi pi. First of all, an inclusive study of B hadrons, pictured on the left in the blue, and then an exclusive B to J psi pi pi k reconstruction on the right. On the left, identifying a displaced J psi and pions, favoring the portion of the J psi rho phase space, and then a multivariate analysis selecting displaced charmonia, minimizing the uncertainty on the measured mass. On the right-hand side, a BDT exploiting that fully reconstructed topology, and then optimization of a Punzi figure of merit. So for the first of those two, the inclusive B reconstruction, we have around 15,000 signal. The momentum dependence of the resolution of the X peak is noted, and so the analysis is binned in those di-pion momentum bins, and then it's separated into 2011 and 2012 data. The line shape for the X is convolved with a resolution function. Its mass is measured with respect to the psi2s to account for any mass scale uncertainties. And then there's a data-driven determination of the momentum scale and the resolution. And we make a Breit-Wigner measurement of the mass and width shown on the slide. The first in passing non-zero measurement of the Breit-Wigner width and a mass that points to a binding energy just positive, a state just below threshold. The main systematics on those two measurements, for the first case, the mass coming from the momentum scale uncertainty, despite being known to 0.03% precision, and then for the width, the modeling of that resolution function convolved with the line shape to give the shapes fitted to the data on the right. But is this a good way to treat the X line shape? Of course, we're dealing with a state right on threshold, and we'll come back to that in just a few slides' time. The second of these approaches, the exclusive B decays. In this case, we perform a two-dimensional fit to the B invariant mass and the J psi pi pi invariant mass, constraining the B and the J psi masses to their known values, which allows us to improve the resolution and reduce correlation between those 2D fit variables. And then again, a resolution model driven by Monte Carlo in this case, scaled with respect to fit to the psi2s peak. And then the main systematics on this determination using this sample for the Breit-Wigner mass and width, coming for the mass from the B mass constraint knowledge, and for the width from the models used to describe the signal and background shapes. And again, a binding energy just positive, and in this case, additional results for the Psi2 3823 mass and width. What about combining those results and looking at the world average? And you see here for the mass on the left, the width on the right, measured with this Breit-Wigner line shape, LECB really driving the world averages with these two new measurements at the top of these two charts. The small overlap between the samples being considered, the world average improves in precision by a factor of nearly 3 to about 60 kV, and it's the first non-zero determination of the Breit-Wigner width, as I mentioned, at about 1 MeV. So then we can go a bit further, and of course the DD star channel in the first of these two papers, the inclusive reconstruction, opens very close to the Chi-C 3872, and so using the Breit-Wigner model isn't the best or as good as we could do. And so what we do is use a modified Flatte model convolved with the resolution function again. And the final fit to data might look rather similar on the right-hand side, but on the left-hand side, you see what's going on with the intrinsic line shape. The Breit-Wigner giving that dotted shape, very broad, and the Flatte or modified Flatte model giving that sharp red peaking structure. So using a more physically motivated model gives you a much clearer picture of what's going on with that intrinsic line shape, and actually a very different measurement or characterization of the width of this state. You see the Flatte full width at half maximum, about 0.22 MeV, 6-7 times narrower than the estimate that one gets with a less physically motivated Breit-Wigner. So a line shape that's telling us more about the underlying physics. What can we learn from this rather complex amplitude that's used to fit the data here? So we consider the amplitude for this Flatte line shape in the complex energy plane. Now opening channels, the DD star, create branch cut singularities in that Riemann sheet. And then the location of poles that are found after the fit of that amplitude to the data on the sheets connected to the state's nature. So for example, a bound state generates a pole on the real axis below threshold on the physical sheet. A virtual state generates one above threshold on the unphysical sheet. A resonance is off the real axis. on the unphysical sheet, and you see some pictographic representation of that on the left. And then you see the data on the right generating the pole. There are two poles, in fact, found in the amplitude, one just off the real axis, which when you switch off the non-DD star open channels and just consider behavior near this DD star, you find a behavior that is bound state with respect to the DD star channel, a probability of a compact component within that state less than 33%. So moving on from the X to absolutely unknown unknowns, and so here a consideration of the J-psi invariant mass spectrum. All observed hadrons, of course, containing so far at most 2 heavy quarks, even thinking to the pentaquarks, but many QCD models allowing CC bar states, and they would be tightly bound given the short range heavy quark interaction involved at play. And these CC bar states have been predicted in mass ranges between 5.8, 7.4 GeV, decaying to a pair of Charmonia. And so that's what we look for. We reconstruct high PT muons above 650 MeV. We look for good track quality, good vertex quality, and then consistent with the 2 J-psis originating at the PV, as you see in the picture on the right. Then we perform a 2D maximum likelihood unbinned fit to the di-mu plane with a rather simple signal description and a background modeled by the exponential, and then a function in the 2D plane which is symmetric under the exchange of the 2 J-psis, and then a really huge signal, around 34,000 signal candidates obtained. It's really very pure, as you can see in the projections of that 2D fit on the right-hand side of the slide. Now we expect resonant J-psi production to happen in a single parton scattering SPS process, and that process should on average generate harder J-psi pair PT spectra than double parton scattering, and so we can consider the analysis in as a function of PT, whether it's binned or whether we apply a cut to the PT spectrum, and we take those two approaches in parallel. And then we subtract the double parton scattering contribution using the high J-psi mass or high J-psi pair mass region. And we obtain the J-psi invariant mass spectrum shown on the slide. We've constrained the J-psi masses to their nominal values. We've required that they come from the PV. And we see these rather unexpected structures. So first of all, a broad structure between about 6.2 and 6.8 GeV, right at the left-hand side of this plot. And then a narrow structure, perhaps more easily identified at 6.9 GeV, and a picture which is clearly inconsistent with a model just consisting of double parton scattering in green and some non-resonant single parton scattering in magenta. So what can we do to fit that spectrum? Well, there are 2 approaches that can be taken. First of all, both approaches include the 6.9 GeV state, and then one or more threshold states, one interfering with a non-resonant single parton scattering, or 2 right on threshold. Of course, feed down could contribute. It's unlikely to generate that narrow state. Near threshold rescattering could be important, and it's the modeling of that that's so complicated. So with those 2 approaches, we generate 2 masses and widths for that 6.9 GeV state, and they're given on the slide with their systematic uncertainties originating either in the modeling of the threshold structure shape in the first case, in the no interference case, and then in the interfering case from the treatment of the PT spectrum, and for the mass from a possibility to include a 7.2 GeV state here. Structures consistent with predicted CC bar states, more data needed to gain further insights. Now we've spent most of the time on those 2 rather detailed studies, but I want to just point very briefly to some rather exciting areas for future study. First of all, using double open charm mesons and 2 recent publications on this topic, and then finally a search analogous to the pentaquark search in J-psi PK a few years ago. So first of all, these open charm states, beauty to double open charm and a third light hadron state. Final states are particularly powerful for spectroscopy. You can look for Charmonia in the CC bar spectra, look for DS states in the D0K plus spectra, and then there are loads of manifestly exotic channels, whether they're DD star charged or D plus K minus, manifestly quark content or whatever. A huge family of decay modes accessible. Now the first steps were taken by the B factories, by Bell in the top for beta D0, D0 bar K, and Babar on the bottom, adding the D0, D minus K plus mode, but limited scope and statistics, and a 50% irreducible background. You see it as that gray hashed shape on the top spectra and the yellow blob in the bottom spectra. The most comprehensive prior study had been a measurement of branching fractions by Babar, but new publications by LHCb measuring branching fractions of beta D star DK processes listed on the slide, benefiting from our particular reconstruction environments. And then you can see these really pure samples, really setting an exciting platform for future studies of spectroscopy for these different D star DK modes on the bottom of the slide. Same for a second publication measuring beta D0, D0 bar K pi, and a quick insight into its resonance structure or its phase space structure compared to a phase space Monte Carlo sample in yellow or orange on the slide. And so you can see interesting potential for spectroscopy in this channel too, and amplitude analysis to follow in both cases. And then finally, that channel that I said was parallel to the pentaquark channel for JSI-PK. In this case, we reconstruct E to C PK. And that's interesting to compare the rate of existing pentaquarks in the JSI proton and E to C proton channels, depending on their structure. And there's even a prediction from one theory group for a new molecular contribution in D sigma at 4.3 GeV, pictured in that cartoon on the slide. And so we carry out an analysis of this channel. An MVA suppresses the combinatorial background, maximizing the working point choice based on a Punzi figure of merit. And you see signal weights obtained from the invariant mass fit, which is pictured in the slide here, on the left for the proton-antiproton PK spectrum, and on the right for the proton-antiproton spectrum, where you see the E to C peak quite clearly. It's the first observation of lambda beta E to C PK, by the way, at 7.7 sigma significance. And then the weights are used to focus on the E to C proton channel on the left for the E to C proton, and on the right for the control mode, JSI proton. And in this case, given the limited statistics, no significant pentaquark contributions were seen, but an exciting channel nonetheless. So a wide range of studies and searches for standard and exotic states with the LHCb detector, many more to come, particularly these open charm final states, and then full exploitation of the run 2 data underway as we expect run 3 in what we hope will just be a few months' time, and first fruits of a rich harvest already at hand. Many thanks for your attention.
Thank you very much, Daniel. So we have one question from Marek. Please go ahead.
Yes, if I understand correctly, in the model with interference for the dicharmonium, it was assumed that the lower Bright-Wigner interferes with the background.
Yes, with
no interference was assumed for the main peak. Can you say a few words about what was driving this way of fitting? Why no interference with the main peak?
Good question. I can't comment in detail. I just say that the modeling of this threshold shape is really clearly complicated by these two methods, and the 6.9 GeV peak is much clearer, much less ambiguous. So I think these two approaches are taken. They might be motivated for the threshold peak, and clearly the 6.9 GeV peak doesn't need that treatment. But I can't comment more than that.
Thank you.
There is another question by Shenzhen Yuan, please.
Yes, we know we have very controversial results on X3072 related to transition to gamma psi prime. I just wonder when LHCb will update the analysis based on a very small data sample.
For the gamma psi prime channel? Sorry, I didn't.
Yeah.
Yeah, I hesitate to put a timescale on somebody else's work, but watch this space and keep asking the question. So we'll follow.
Thank you.
These are challenging channels, of course. Reconstructing the psi prime gamma is a major challenge for LHCb, where neutrals are not something we're designed to do, but we achieve success at nonetheless. But that's a challenging mode for us.
Are there other questions for Daniel? Okay, I don't see any, so thank you, Daniel, again. Let's move to our next presentation by Sen Jia. Sen, please go ahead and share your screen.
Use my screen.
Yes, we can. You can start.
Yeah. I will give a talk on the start of conventional and non-conventional hadrons at Bell. As you know, Bell is electron positron colliders. It's in KEK, Scuba Center, Japan. The closing mile is 22 miles. And the red plot shows the barrel detector configurations, including the PSD system and the PID system, including the single drift chapter, QRM, ACC, etc. The data taking at Bell is more than 10 years. The collected data on, off, and scan Umslow peaks. The total luminosity at Bell is more than 900 inverse F bar. We have more than 700 million BB bandwidth to study the B physics. Here, I would like to show these results from conventional hadrons and non-conventional hadrons at Bell. For conventional hadrons, I will talk the Umslow vars to gamma Chi-1 and search for eta C2 1D and omega eta B vars to S transitions. For non-conventional, I will talk about the Y46, 26 to DSDS1, DSDS2, and search for X3072 in 2 photon reactions and search for R++ to D+, DS star plus. Here I will show the results on the observation of relative decay of bothmonium to trimonium Chi-1. Here is a novel method is applied to tag the Umslow vars while Umslow twice to Umslow vars pi transition to suppress the SR and SR backgrounds to increase trigger efficiency. Here we use the largest Umslow twice data samples in E colliders. From the left plot, we can see very clear Umslow vars signals. The signal is very huge, and the dashed lines shows a required signal region. The histograms show the background from the E set2S SR process backgrounds. Thus also started the momentum of Chi-1 gamma pi. From the right plot, we can see if we require the momentum of Chi-1 gamma pi less than 100 MeV, the background from the SR process set2S and the mu S FSR process can be reduced efficiently. Let's see the results from the plots above. We can see a few of Chi-1 waves observed. The dashed histogram shows the upper limits on Chi-2 signal use by performing the simultaneous phase to environment of gamma deep psi. The significance of this channel is about 6.3 sigma. To identify the background from FSR, mu, and FDR set2S signals also started the waves from deep psi bands and bands requirements for the pi set-bands. We can't observe signal waves around the Chi-1 signal region. Finally, the Bragg fraction is calculated to be 4.7 times 10⁻⁵. This value is slightly higher than the previous results and much higher than the theoretical predictions, which may indicate the enhancement of Chi-1 formation from the initial vector state with emission of the photon. Using the BB bar waves collected at Bell, we perform the analysis of Chi-2 1D search in B decays. Actually, at Bell, we have reported the evidence for B2 psi2 1D, psi2 1D to Chi-1 gamma. The eta psi2 1D and eta C2 1D are very close, and the Chi-2 1D is expected to decay predominantly while E transition to gamma HC. In this analysis, we use 4 channels to search for eta C2 1D states, and eta C is tricky started by 10 moles. To suppress the background and increase the efficiency, we apply the multivariate analysis based on the neural network, and a global optimization is performed. From this 4 environments spectra for HC gamma, we can't observe any eta C21D signals. The red histogram shows the fixed results with the largest significance. Since we observed any signals here, we give the 90% upper limits on the product branch fraction. They are at levels of 10 to minus 4, 10 to minus 5. Using data samples collected Wumsong 4S and 5S resonance, we search for Wumsong 5S and 4S 5S to make eta B transitions. Here, from the molecular model, the branch fraction of the Wumsong 4S to eta B1S gamma is similar to that from Wumsong 4S to HB1P eta. Here we search for eta B1S from Wumsong 4S decays, from Wumsong 4S and 5S decays, and search for eta B2S from the Wumsong 5S decays. We restart the omega by the 3-pi mode and identify the signals in the required mass of the omega. Let's see the results. This 3 plot shows the required mass of the pi plus, pi minus, and pi zero for 3 channels. From this inverted mass spectrum, we can't observe any eta B1s or 2s signals. Note that the red solid histogram shows the nominal fit results, and the red dashed histogram shows the upper limits. Here we can't observe the eta B1s and 2s signals, so we give the 90% upper limit on the branch fraction for the 3 transition decay modes. They are at levels of 10 to minus 4, 10 to minus 3. The suppression of the Wumsong 5S to make eta B1 transition related to Wumsong 4S to eta HB1P could be due to the different overlays between the initial state radiation state and the bottom in the final state, or the details of the eta and omega methane production. Okay, let's move to the non-conventional hadrons at Bell. If you extract the events from the Y4260 or Y4660 signal regions and then to the environment mass of the pi, you can see many events are accumulated at the F0918 signal regions. Since F0 has a SS bar component and GPSA has a CC bar component, so it's natural to search for the Y states with a component, acquired components of CS bar, SS bar. Those are DS, DS1, DS2, DS2. In this analysis, we applied the NOVA method. Here we only restart the ISA photon, DS, and K or K short, and identify the signals in the required mass of the ISA photon, which equals to the environment mass of the DS1. Since the energy momentum of the ISA photon is very bad, since its energy is very high. Here we restrain the required mass ISA photon DSK to be the nominal mass of D star to improve the mass resolution. The data samples used here corresponds to more than 900 inverse F bar. Here I will show you the results on the E to DS1 channels. In the remark mass of the DS1, we see a clear peaks around the threshold in the remark mass DS1. One possible background is from the E to DS star DS1, and the photon from DS star is missing. So we also started these channels, and we don't observe any significant signals in DS star or DS1 channel. Here we consider 4 components for in the phase: signal DS1 by side bands, the DS star DS1 background contribution, and the non-resonant contribution. The results are listed in this table. Here, let's move to the results on DS star decay channel. Similarly, as in the close to the threshold, we also reported an evidence for E to DS2 states. Here we consider three components in the simultaneous fit signal DS2 method by the non-resonant contributions. Also, to start is a possible background from the DS star DS2. We also study its channel and no significant are observed. Here, the result list in the table. So we have a question that is the Y46 30 is Y46 60. We compared the states around these regions from different final states, lambda C, pi psi 2s, DS1, DS2. The mass of these states are very close. You can see the results in the table, and the widths are relatively large. So maybe these states will be the same one. This need the measurement with improved precision to verify this. Then I will introduce the results for the search for X3872 in Papa chip psi in signal tag to photon interactions. As we all know, the gamma to X3072 is not allowed, but if one or both photons are highly virtual, we can search for X3072 into a single tag to photons. In the analysis, we restart the electron and the chip psi, as well as the pi plus pi minus. Here, we use data samples more than 800. It was F-bar. Let's see the result. In the X3072 signal regions, we observed 3 events here. After considering the backgrounds and embedding the Feldman-Cousin method applied, finally we gave the signal use is 2.9 with a significance of 3.2 sigma. The gamma partial width times X3072 to pi by psi is about 5.5 eV. This result can be compared to the theoretical results to identify the nature of the X3072. Let's see the analysis of search for the R plus plus to D plus DS star plus. Here is the preliminary result from Bell. The R plus plus is a state of doubly charged and doubly charmed molecular states. These states can also be a good candidate for doubly charged Tyndall quark. Here we also use all data samples to perform this analysis to search for this state. This 5 plot shows the environment D plus DS star plus from 5 data samples. Here we don't observe any significant signals. We give the upper limits with the mass varying from 4.13 to 4.17 and then width varying from 0 to 5 MeV. The limits are the branch limits are shown in this table. Here, I would like to give a summary. Although the Bell has stopped data taking for 10 years ago, we have producing exciting results. In this report, I introduced the first observation of radiative decay of bothonium to charmonium and the first vector charmonium-like state decaying to charmed, anti-strange and anti-strange charmed meson pairs DS1, DS2, and we also reported the first evidence for X3072 to Papa chip psi, the single tag to photon interactions. As we all know, the Bell 2 will reach 50 watts EBA, which will provide a great sensitivity and precise measurement in Hadron physics. Thank you for your attention.
Thank you very much. We have time maybe for one quick question. If you have questions, please raise your hand. Don't see any questions, so thank you, San, again. We'll move to our next presentation by Roberto Musa. Roberto, please go ahead, share your screen.
Yes, I'm here. I'm just Okay. You see my screen?
Yes.
Okay, fine. Thanks for inviting me. I'll just give a brief report about the startup of Bell 2. To promise, GSM just promised that we're going to have 50 inverse October in the next 10 years, and we're still crunching the data of the previous of the 10 years where we took data in 2000 to 2010. So let me just say that Bell grew up pretty much. Now we have a collaboration of more than 1,000 people from 29 countries. We enjoy the start of the run right now in the competition with LHCb. I hope that will push us to do as many results as we achieved to make during the first generation of B factories. So far, we got essentially, we accumulated 74 inverse femtobarn in the phase 2 and phase 3 of data taking from last year to this year. Only about half of it, which is about 38 inverse femtobarn, have been processed completely to provide the ICHEP dataset, and I will show simply some result of reconstruction of vector Charmonian, Bottomonian, and pseudoscalar mesons from this sample. Is just starting to take valuable data. We have been able to run through the COVID crisis with reasonable success. Of course, we had to change a bit our habits and distantiate ourselves. We have been getting used to take data from our living room instead from the control room with many remote shifters. This allowed people to work safely, and machine guys were able to turn on the crab waste sextuple, reducing significantly in the background, and allowing to reach already our first result, which is the luminosity world record that we set. We beat in June 15 the 2.05 10 to the 34 record established in 2010 by KEC-B. And we now reached a maximum 2.4, and we're expected to increase a lot during the next year. So what are the XYZ states? You already got a number of presentation about these things, and I'm sure that all the people that are in this session know quite well what we are. Let me just remind that when we started the previous generation in the year 2000, essentially we were puzzled about completing we were worried about completing the puzzle of understanding all the standard quark-onion pair states. Essentially, the parabottom-ionia were completely unknown. That task have been successfully achieved by the B factories, but besides these, a number of states have been found that were not completely understood. Some of these were charged and opened the question of their interpretation. A huge number of discussion and papers were produced in this year. There are, I here suggest a number of review paper on all the subject and on specific interpretation. And you can browse the QWG website for all the conferences we organize on this topic. The beauty of the beauty factory is come for the fact that we can observe these exotic state in a number of ways, not just with BDKs and initial state radiation, but also through the double charmonium process and in gamma-gamma collision, where we started seeing things that were not seen before. These kind of pattern were already shown a number of times, applies for both charmonium and bottomonium. So as I was saying, I mean, right now we are just at the beginning of the thing. I mean, if you just want to overlap the history of the discovery of this exotica, you may notice that the first discovery, the X3872, was announced after a bit more than 215 femtobarn by Bell in 2003. As I was saying, we just accumulated something like 70 inverse femtobarn, so we are about here. And I must say also that the COVID crisis allowed also machine guys to make progress in understanding how much we can get from our machine. So we learned that beside the known scheduled shutdown on 2022, we're going to have another shutdown in 2026. And we are probably hoping to get to the first inverse actoman, which is this trip, only just before the 2022 shutdown. For next summer, we are hopefully going to get to scratch the edge of observation of X3872. And we are considering now the possibility of running at 10.75 GV, where we have found some interesting stuff in analysis of data taken during the high energy scan. As Jasen was saying, many things were discovered up to 10 years after the end of data taking from the factories. Now, we have, I was just to prove that we exist. I mean, I'm going to show some recent result. This is from the ICHEP data set of, this is observation of B2 Psi-K, both in EE and mu mode with simple cuts. Of course, we are working on trigger efficiency and such, and acceptance. This just show comparison with, no, this is just data and the fit to the data on a B-enhanced data sample. So this is J-Psi. This is Psi prime from actually a data sample from early phase 3 and phase 2. This is with B going to Psi pi pi. Of course, we have a larger data sample right now, not ready yet for presentation, and the goal is to come as soon as possible with the data to the discovery of the X3872. Again, we have signaling both E plus and minus and plus and minus mode. We have seen the amazing new result by LHCb, which constrains the limit on the total width of the X3872. These are simulation about what we can do in the DT star modes with the full luminosity that we plan to achieve in the next 10 years. And also we have been seeing, a couple of days ago, July 29, that Babar already kind of measured the absolute branching pressure of B to KMX3872. I would say that the situation is quite a bit in tension with what we got with almost twice the statistics, where we essentially could not claim observation of this specific state. And also I see here that the situation is a bit confused by probably some other states. So we really need to take something like 1 to the 5 inverse actoban in order to understand what we're saying, I would say. To proceed further, of course, the ISR also is being tested. We have production of initial state radiation from with just a mu mode with just a simple cut on the recoil mass in order to select clean objects recoiling on a photon. Also, work is ongoing on checking trigger efficiency using the angular distribution. These are results just approved from the ICHEP data sample again. With the Psi prime as well, we have an early set from the phase 2 last year, and we have now to compare this with what BESS is doing. They already reached a comparable luminosity on the range of BEL2 in 2026. So we are really pushed to get as much as we can, especially in the region above 4.7, where BESS is not yet succeeded to arrive. Of course, same thing is ongoing for bothonium, and it's we already detected epsilon 2s and 3s in mu pi pi that here you can see from early data sample. And another thing which is relevant to do for bothonium, I mean, we are kind of trapped to almost stay at the 4s for at least the next inverse octoban. We have very few chances to get elsewhere. And let me remind you that during Bell, actually later than after the discovery of the eta B through radiative transition from 3s and 2s, we found out that the largest hadronic cross-section to lower botomonia is not through a dipion transition. It is from an eta transition to HB, which subsequently decays to eta B. So this is our main pathways. You notice 20 versus 1.8 to eta 1s and 0.8 to pi pi 1s and 2s. So essentially, we have that the largest data sample of eta B for the next, say, 3, 4, 5 years will come from this transition, and we'll see how much we can squeeze on the nature of the eta B from this data set. Moreover, in Bell, we discovered the eta prime transition to the 1s that we will further want to study. For this, what we need is to detect cleanly inclusive eta and eta prime mesons, and here you see eta reconstructing gamma gamma and 3 pi mode, and again eta prime reconstructing eta pi pi in this and eta going to the same K mode. So you see that we can see quite clean sample of these. Moreover, as I was saying, we don't have many chances to run outside the 4S for at least until before 2022. We were envisioning running at the 6 sets, but this is just on the edges of the phase space, and we essentially have no spare cavities. The accelerator people have no spare cavities to run safely there. So we may do just a test run there and focus on running a bit below the 5S at 10.75, where we see that there is sort of a bump or a kink that we dubbed YB10750, and already has triggered a number of theory paper about possible interpretation from, as usual, from conventional botomonia to more exotic kind of interpretation. And you have seen a talk also a couple of days ago about this by theory. So for this, we need just, say, 10 inverse femtobarn to shed light. This is just, we have just one point. The rest is actually, the blue point are actually obtained from analyzing ISR production from the much more larger sample from this energy. And so we'll have to take a few points here in order to clarify the nature of this state. And to finish, then I would say that yes, we get only 74 inverse phantom bands so far. Expect some results, really rediscovery starting from next year to the 2022, where we really rescan through the discovery of all the first generation of the factories, and from there on, as we assume to have 50 times the statistics. I really don't have the crystal ball, do not know what we're going to discover from that. And of course, we will really enjoy the competition with LHCb for the future 10 years. That's it. Thank you very much.
Thank you very much, Roberto. We have time for a quick question by Marek. Please go ahead.
Hi, Marek.
Roberto, good morning. I just want to point out that Bell 2 has a unique opportunity to measure something that probably nobody else can do. And this requires stretching your energy range a little bit. These are the bottom analogs of D sub S 2317 and D sub S 2460.
And we should go where? What energy?
You should go around 11.132 GeV.
Which is a bit of a stretch.
I know.
And it's good to have a theory, how can I say, request, because I mean, and strong motivation to do this kind of request, because of course it's money. Yeah? It's not, I mean, any upgrade is money.
I want to stress that this is not really theory, because these states are very well understood, very well measured experimentally in the charm sector. And there is very little doubt that they exist in the bottom sector. So this is a sure bet, and probably nobody else can do this.
We'll definitely benefit from any plethora of states of studies theoretically stressing the importance of understanding these objects to push the physics case to run at higher energy. I mean, we have been struggling a lot. Even, I mean, we were hoping to get a success, but right now, I mean, they really have to buy new cavities in order to guarantee a safe running at a success. So can you imagine that? So it's just a matter of money and physical push. I mean, there are many reasons for running.
I will send you a reference.
Okay.
Thank you very much. I think we need to move to our next speaker, Siyu Xiang.
Thank you.
Thank you, Roberto. If you can go ahead and share your screen, Siyu.
Yeah.
Very good.
Can you see my?
Go ahead. Yes, we can see your screen.
Perfect. Hello, everyone. The topic of this report is Quaternia and the B sub C related study at LCB recently. Several new results since the last ICHEP meeting are selected. The heavy quark production cross-section is higher at LCB, plus LCB is a special detector with excellent momentum resolution, particle identification, decay time resolution. So it's very nicely to study heavy flavor physics. And we collected 3 and 6 inverse phenobar data for run 1 and run 2. The quaternia can be produced by central exclusive hadron production, namely CEP. At LCB, the recently CEP results measured with JEP psi and psi 2s, as shown in right plot. The combinatorial background from QED persists. The measured JEP psi and psi 2s differential cross-section are better agreement with the next 2 leading order predictions. This result has reported at the last ICHEP meeting. For inclusive quaternia production, it can be factorized to short and long distance effect, where the long distance matrix element from experimental data. The related theories have color singlet model and NRQCD. Chamonix hadron production is not completely understood, while optional give better agreement with NRQCD predictions due to heavier mass. The first ETA-C parameter hadron production measurement at 7 and 8 TeV using ETA-C to PP bar channel. The color singlet leading order prediction predicted the result will, but below expected color octet contribution. Theory description has impressive progress integrating RCB results in long-distance matrix element calculations. So the ETA-C parameter hadron production further measured at 13 TeV relative to JEPSI to reduce uncertainties. The parameter and the BTK components are separated with pseudo lifetime TZ, which is Chamonix flight time projection in collision direction. The left two plots cut TZ to separate parameter over BTK Chamonix, and then fit the mass spectrum to obtain ETA-C over JEPSI, while right two plots extract the errors from fit to TZ, and we get consistent results. The first ETA-C production measurement at 13 TeV in agreement with the color singlet prediction. Here also present ETA-C and JEPSI parameter production dependent to central mass energy. The latest one is the measurement at 13 TeV. With present statistics, no dependence on the parameter production ratio between ETA-C and JEPSI observed, but the differential parameter production ratio depends on the PT obviously. In addition, we have more precise measurement of the ETA-C inclusive production in BDKs. The next is the PSI2S production at 7 and 13 TeV. For PSI2S, the phase down effect is negligible compared to JEPSI. Both for parameter and BTK PSI2S production have measured at 7 and 13 TeV. We use the same TZ fit as ETA-C analysis to extract parameter over BTK component. Here show first the total production cross-section for parameter and BTK PSI2S at 7 and 13 TeV. Then is the double differential cross-section from 2D fit in beams of PT and rapidity Y. Differential cross-sections overall good covered by predictions by with deviation at low PT for parameter PSI2S, as shown in left two plots. And the new measurement at 7 TeV supersedes earlier results based on smaller event example. This work presents the production ratio between the PSI2S and JEPSI as shown in left plot. Also, the PSI2S production ratio between 13 and 7 TeV shown in the right plot. Both these two plots are important to extend the theory prediction to lower PT range. Apart from production measurement, RCB also observed a new narrow Chamonix set X3842 with detached DD bar candidates using 4 run 1 and run 2 data. This analysis obtained about 3.5 million D0D0 bar and 2 million D plus D minus candidates. D measure mass required in 20 MeV difference from PD value can significantly improve the signal purity. Then constrain D measure mass to the known values to improve the resolution. As shown in right plot, a peak around 3842 can be seen clearly. Then the mass spectrum fit is performed in 3 ranges due to complicated backgrounds. The simultaneous fit is performed for D0, D0 bar, and D plus, D minus samples. A new quaternion obtained. The mass central value is 3842 MeV, and the narrow width is about 3 MeV, which are compatible with the precise 1D harmonium state, with the JPC is 3 minus minus. In addition, this analysis first observed the parameter hadron production of the psi 3770 and the psi 3930. The measured psi 3930 mass and width have 2 sigma deviation from PDG value. Apart from quaternion study, the B-sub-C method has rich spectroscopy allowed to prove quaternion-based QCD model, but less explored due to limited statistics. So let's search for excited B-sub-C method, begin with B-sub-C2S. In theory, the energy of basic B-sub-C2S states is lower than B method and D method threshold, so it can undergo Olin cascade radiative or pionic decay. Atlas first observed excited B-sub-C2S, but cannot resolve it. Last year, CMS resolving it to 2 excited states. Meanwhile, LCB has observation. RCB reanalysis almost run 1 and run 2 data, about 5 times more than previous run 1 analysis. A clean B-sub-C example with JPSI pi final states obtained as shown in left plot, about 4,000 candidates. Then we require large PT for the final B-sub-C and small energy gap between B-sub-C2S and the final states. Finally, LCB observed B-sub-C2S star with significance larger than 5 sigma. Also hint for B-sub-C2S with global significance 2.2 sigma. Even our B-sub-C2S signal is less than CMS, but the mass resolution is more precise. One can see the right plot and the CMS result. LCB has a smaller mass resolution. The mass measurement of B-sub-C2S and B-sub-C2S star are the most precise so far. The dominant uncertainty comes from the PDG value of the B-sub-C mass. Therefore, next is the precision measurement of B-sub-C mass, which first reported today. With 4 LHCb datasets, merged 8 channels to obtain the largest B-sub-C examples. The 3 dominant contribution, JPSI pi, JPSI 3 pi, and JPSI D sub S, are shown here. The different channel results are combined with the blue method. Finally, most precisely measure the B-sub-C mass. The uncertainty is about 0.3, smaller than PDG value 0.8. This work also combined the D sub S pi and the JPSI phi pi 2 channels, measured the mass difference between B sub S and B sub C. Further to excite the B-sub-C measuring state, what about search for KBC0, which also contains 2 different heavy quarks? The first doubly heavy baryon CC was observed at RCB. The BC mass is predicted to be around 6.9 GeV and a lifetime from 100 to 300 femtoseconds. A preliminary result of first 34 0 in D0.10 final states shown here. Regretfully, there is no observation, so set up limits on production ratio related to lambda b with the same final state as a function of mass for different lifetime hypotheses. Okay, finally, a quick summary. First, eta C parameter production measurement at certain TeV. The result in agreement with the color singlet model. More precise measured inclusive production in bit case. The second is more precise measured precise 2S production at 7 and 30 TeV. This work extend the theory prediction to lower PT range. The observation of parameter production narrow harmonium X3842 in DD bar channel, which is precisely 1D harmonium. And this work also obtained observed the parameter Hadron production of psi 3770 and psi 3930. RCB observed excited B sub C 2S star. Mass measurements are most precise so far. And the most precise measurement of B sub C mass also presented. And the RCB also do the first search for doubly heavy baryon BC and the up limit set. Thanks for your attention.
Thank you very much for this very nice talk. So we're back on time and we have time for a few questions. So please go ahead. There's one by Sada Aru, please.
I have a question on the DD bar spectroscopy on page 12. And yes. In this analysis, how do you process the possible decays from the DD star bar, which can decay into DD bar pions, which may make also a resonant peak in the DD bar mass spectrums with some separation of the 140 MeV. My point is that the DD star bar decay of the Chi-C2 3930 can make a peak also near the location of the psi 3770. So how do you consider about such a possibility?
I'm not sure, but I guess we constrain the mass window to exclude the D-star candidates.
Hi, this is Marco. So if I understand it correctly, your question is that the partially reconstructed decay of the Chi-C2 can peak somewhere else, right? So this kind of feed down have been considered and they have been excluded. So this is something that has been explored actually.
Thank you very much.
Are there any other questions for our speaker? Yes, Roberto.
May I ask if you can, with more statistic, put in evidence if there is both a prompt and a non-prompt decay that form the X3842, in the sense that if there is also some B to X3842 decay ongoing production mechanism?
Yes, the analysis evaluated with also with the TZ fit measured and found that the efficiency for bit decay is negligible. So the production is probably from prompt production.
Okay, thank you.
Okay, I think we should move on. Thank you, Ziyu, again. We'll move to our next speaker, who is Karin Schoening. Please go ahead.
Good morning. Now I'm sharing my screen. Do you see it?
Yes, go ahead.
Okay, great. Good morning. My name is Karin Schoening, and I'm going to talk about polarized and entangled hyperon-anti-hyperon pairs in BESS3. And this is the outline. I will start with an introduction, briefly present the BESS3 experiment, and then I will talk about hyperon structure and hyperon decays and conclude with a summary. Many challenges in modern physics manifest themselves in the nucleon and our difficulties in understanding it from first principle. For example, the abundance, there are much more nucleons than antinucleons in the universe, but also its mass, its spin, its structure, and its radius. And in this talk, I will focus on the abundance and the structure. And when you have a system that you don't understand so well, a common strategy is to make a small change to the system and see how it reacts. So for example, you can scatter on it, which you do in different kind of structure experiments. You can excite it, which is what you do in spectroscopy, or you can replace one of the building blocks. So instead of having a nucleon, you can replace one of the quarks with a heavier one, for example, a strange quark, and get a hyperon. And the advantage of hyperons is that the polarization is experimentally accessible. And this is thanks to the weak parity violating decay. So for instance, a lambda hyperon decaying into a proton and a pion, then from the angular distribution of the decay proton, you can deduce the polarization. And this is useful for many reasons, as we will see in this talk. So we have two fundamental questions to understand the strong interaction and how hadron structure emerges from this. And we have the fundamental symmetries. Then we use hyperons as a diagnostic tool to study these two questions. And from this, two main topics emerge: hyperon structure and hyperon decays. And this is something we study with the BESS3 detector at the Beijing Electron-Positron Collider. It is optimized in the Tau Charm region, but it covers the full range from 2 GeV up to 4.7 GeV in CMS energies. And the Beijing spectrometer, or the BESS3, has a coverage of nearly 4 pi, and it offers tracking, particle identification, and calorimetry. And it has a very broad physics scope. There are many other talks about the BESS3 experiment at this conference. So let me start with hyperon structure. So hyperon structure, or hadron structure in general, can be quantified by electromagnetic form factors. And these are analytic functions of the momentum transfer squared of the virtual photon that always participates in processes where you study these form factors. And in the space-like region, so space-like form factors that you see here to the left, they are sort of intuitive to understand because they can be related to charge and magnetization densities, for instance. But these are difficult to access for any hadron that is not stable because you study it in elastic scattering. So for unstable hadrons, you instead look at the time-like region, which you see to the right. So this is what we have when we want to study hyperons. And in BESS3, we can study electron-positron annihilation into a virtual photon with the subsequent production of a hyperon-anti-hyperon pair. And space-like and time-like form factors can be related via dispersion relations. And something particular about time-like form factors is that they can be complex and have a relative phase. And this phase is accessible via this measurable polarization of the hyperons that I told you about before. Another interesting thing about the phase is that we are interested in the asymptotic behavior of the form factors. So at large momentum transfer squared, the space-like form factors should approach the time-like. For nucleons, the scale where this happens can be checked by simply measuring the space-like and the time-like form factors and compare them. But this is not possible for hyperons. But since we can measure the phase, we can check the onset of this scale by simply checking when the phase approaches 0, because space-like form factors equals time-like form factors means that the phase needs to be 0, since the space-like form factors have no phase because they are real. So the hyperon polarization offers an alternative way to study this asymptotic behavior of the form factors. And recently there was the first complete measurement of the lambda electromagnetic form factors. So these were studied in electron-positron annihilations with BESS. And the formalism for this is presented in brief on this slide, but also in the article that we refer to. So for spin 1/2 baryons, the angular distribution can be completely parameterized by 2 global parameters: the angular distribution parameter that we here call eta, and the phase delta phi. So the angular distribution has an unpolarized part, a polarized part, and a spin correlated part or an entangled part. And and it depends on 5 different angles that you can measure. And since we measure in each event 5 angles, we have lots of information in each event. So in a relatively small sample, so this sample of 555 lambda bar events that we have collected with BESS3 off resonance at about 2.4 GeV, we were able, with this formalism, to measure the ratio of the form factors that you get from this angular distribution parameter, but also the first measurement of the phase and also the most precise measurement of the cross section so far. And this was published last year in Physics Review Letters. And there are already some theory interpretations of this. There were theory calculations several years ago by Heidenbauer and Meissner. So these were based on final state interactions with potentials from PP bar data from Lear. So these are true predictions. So they emerged earlier than our data. Then there have been some recent calculations using vector meson dominance and also some calculations using dispersion theory. And the first 2 of these are presented here with dashed lines and red lines, and along with data from Babar on the ratio of the form factors and also the blue point that corresponds to the BESS data. Now I move on to hyperon decays. These are a useful search ground for physics beyond the standard model at the precision frontier. And hyperon decays occur as an interplay between weak or possibly beyond standard model interactions and strong processes. But this means that these non-perturbative strong effects may hide CP violation. In 2-body hyperon decays, one can, though, define quite clean CP symmetry observables. So when you have these 2-body decays, you can quantify the decay by a decay parameter, for example, the alpha, and that is accessible in a direct decay. And if we have CP symmetry, it means that the decay asymmetry parameter alpha of the hyperon equals minus of the corresponding asymmetry parameter of the anti-hyperon. So you can define a CP observable by an asymmetry of these 2 decay parameters. And for this, for measuring this, we can use the same formalism as we used for the structure measurement, but here we do not use the constraint that CP symmetry is conserved, so we get a few more terms. But we still have this unpolarized part, a polarized part, and a spin correlated part. And we measure the 5 angles just like before. And for this, we use a new BESS measurement with more than 400 events of lambda decaying into charged pions and protons, and the same with lambda bar, and about 47 events where the lambda decays into a charged mode and the anti-lambda into a neutral mode. One of the most striking results in this measurement was that the value of alpha, the decay asymmetry parameter, was 17% larger than the old PDG value. And now the PDG value has been updated. And we also managed to calculate the most precise CP test for the lambda decay so far. And to the right, you see the polarization as a function of the lambda scattering angle for the charged mode and the charged neutral mode. And these were published in Nature last year. There is also a recent measurement where we have studied the sigma plus hyperon decaying into proton and a pi zero. And these were studied both from sigma plus sigma bar minus final states from J psi decays, but also from psi prime decays. And here an interesting result is that the phase of the hadronic form factor in the J psi has the opposite sign compared to the psi prime. So this needs to be understood. This is a bit remarkable, actually. We also provided the first CP test of the sigma plus decay so far. And these have been published on the archive and accepted by Fürstev letter. In sequential hyperon decays, meaning hyperons that decay into other hyperons that then decay, we can access even more information, because then we can measure other decay asymmetry parameters like the beta, gamma, or the phi. These are not independent of each other, but in principle, one or two of them is okay to completely determine the decay. And then you define the CP symmetry as, for example, as beta of the hyperon equals the minus beta of the anti-hyperon, and so on. And then you can again define these CP observables as asymmetries of these parameters. And if you combine the information from, for example, the asymmetry A and the asymmetry B, then you can pinpoint the weak or possibly beyond standard model amplitude and separate it from the strong amplitude. And this means that you get more sensitive to a possible CP violation. And we have started some measurement of sequential hyperon decays. One is a single tag study of the lambda charm in several different decay modes. But since this was a single tag measurement, we couldn't study any spin correlations. Here, we found an indication of a non-zero polarization, very close to threshold at 4.6 GeV. We provided the first measurements of the decay asymmetries for the proton kaon decay and also the sigma 0 pi plus decay, and improved the precision for some other decay parameters. This measurement also served as a proof of principle for measurement of beta and gamma. And if we can find a point where the polarization of the lambda C is larger than here, close to threshold, then our method will be more sensitive to the parameters beta and gamma, and we will get an even better measurement. We have also recently studied the spin properties of the omega baryon. This was studied in psi prime decaying into omega bar. And the omega bar is a spin 3 hyperon, so it is a bit more complicated to describe it. You need 4 form factors or helicity amplitude to describe this process. And we have studied it in a single tag study. Here we have extracted helicity amplitudes, but also the decay parameter phi of the omega to lambda pi decay for the first time. And from the polarization parameters that we can extract from these helicity amplitudes, we were also able to determine the degree of polarization, which is the square root of the square sum of these polarization parameters. And there were two solutions provided by these measurements, and these are shown here in the bottom. And these results have been published on the archive and submitted to PRL. Then there are some ongoing studies. We want to find the scale of the onset of this, where the onset of the scale where the space-like and the time-like form factors approach the same value. And this we study by measuring the phase dependence on the energy. And this is ongoing. We also study the phase of other hyperons in off-resonant low energy scan measurements. Then we have a world record sample of JAPE size in BESS3, 10 to the 10 JAPE size to be more specific. And from that we can study, we can make these large scale tests of sequential decays like sigma 0 and also cascade hyperons. And we can study these hyperons in exclusive measurements and double tag and study the polarization and the entanglement. And we have dedicated model independent formalisms that are developed for this. So to summarize, hyperons provide a powerful diagnostic tool to study both the strong interaction but also fundamental symmetries. And we have new measurements from BESS3, where we make a complete measurement of the lambda form factors, precise tests of CP symmetries in lambda decays, new studies of sigma plus, omega minus, and lambda charm, and lots of ongoing large-scale studies. Thank you for your attention.
Thank you very much, Karin. Very nice overview talk. We have a few minutes for questions. Please go ahead, raise your hand if you have questions. I guess everything was clear. Don't see any questions, so thank you, Karin, again.
Thank you.
We'll move to our last presentation before a short break, which will be by Michal Krelina.
Hello, do you hear me?
Yes.
Okay, I will start to share video and my screen. Okay, is it working?
Yes, go ahead.
Okay, thank you. So hello or good morning. So my name is Michal Krelina. And first of all, I would like to thank organizers for this opportunity. And after a series of experimental talks, so it will be a little bit more theory, specifically on heavy quarkonia and theoretical approaches how to calculate the wave function for them. Okay, so there is an outline, so some motivation introduction, then I will describe how to calculate the vector meson or quarkonia wave function properly. Shortly, I mention their production, ideal for study the wave function. Then I will explain the problem of the selection for the vertex. Then I, for real comparison with experimental data, we set some scenarios and compare each other, some numerical results and conclusions. So the vector meson and specifically heavy quarkonia like JAPE psi and upsilon, for example, from my point of view, they are very interested as the probe for heavy ion collisions because they can serve as the like temperature of the hot and dense matter, but actually there are many more interesting application of these quarkonia. So usually we assume in most cases we are interested about the 1s states or heavy quarkonia, JAPE psi and upsilon. Of course, there are higher states like 2s psi prime, or in case of upsilon, it's usual to have psi upsilon, 2s or 3s. Especially, I'm very interested in heavy quarkonia because their size is quite small, and the way how we calculate their wave function allows some simplification if they are, in case they are heavy. However, the main question is, in most of papers that deal with the wave function, typically for example, for incoming electron ion colliders or general or LHEC. Most of the publication you can see that they use the boosted Gaussian Lycon wave function. That is actually quite old theory, but today is much more overcome. So there are problems about the vertex that I will mention later. There are other simplification like only harmonic oscillator potential between QQ bar. So how to get the wave function really properly? So basically, in case of heavy quarkonia, you go in the rest frame. So in that case, you are in the classical quantum in quantum mechanics, not the relativistic, but let's say slow. And there is some interaction between QQ bar, and you can solve it by Schrödinger equation. You will get some wave function. And that wave function you can use to your frame. In my case, to Lycon, because I work on a diaper framework. Because later I will compare my result mostly with the diffractive result. So for that reason, color dipole framework is the best application. So, but there are small some details in this calculation. So first of all, it's like three-dimensional. So we need to consider the radial part and spin orbital part for calculation. Fortunately, in case of vector mesons, generally we can factorize them, that we can separately calculate the radial part and separately spin orbital part. In most cases, people usually omit the spin orbital part. Usually, if they try to justify, usually by something like it's hidden in normalization because there is some overall normalization of the wave function. And again, the function there is a note about the harmonic oscillator. So here they consider only harmonic oscillator that potential that is not. It's a good approach, but not so much realistic. For example, it doesn't include Coulomb repulsion, or also they don't consider any spin orbital effects. Okay, so in case of radial part, it's simply Schrödinger equation. There are on the market, there are different, except the harmonic oscillator potential, some realistic from experimental data. And the more interesting part is how to incorporate the spin orbital part. Actually, it's a more complicated, but however, quite long time ago, H.J. Melosh found a relation between the spin orbital part in the rest frame of heavy quarkonia and the Lycon frame. So he derived such a matrix, Melosh spin rotation matrix, that allow you incorporate this spin orbital effects in your final Lycon wave function. Pardon. Okay, so there is very short note about the final calculation for some observable. As I said, if we want to really study the wave function in details, we need to the most clear probe. So one of the, from our point of view, is the diffractive electroproduction of the vector meson. So there is, you have some virtual photon that fluctuate in QQ bar and that create the considered vector meson. And for that is the best tool you can use is color dipole framework. Okay, let's see more details about the Lycon wave function. So basically, there are some constants like alpha electromagnetic, some pi, and overall normalization factor. Then we have some vertex factor. So we have some spinors, some vertex. This vertex saying that the QQ bar goes in the our vector meson. and R represents the Meloy spin rotation, and then we can factorize with the radial boosted into radial wave function boosted to the Lycon form. So basically, what are options or the most commonly used options are for the vertex. You can consider the massive photon-like vertex. So this is like typical vertex. If I return here, photon goes to QQ bar. It's exactly the same form of the vertex, but there are some problems that I will refer to later. Or you can, the most proper way, I will also explain later why, is to use like only first term that will generate only S wave in the rest frame, because here you are getting the D wave contribution to your vector meson. And also about the Meloy spin rotation, you can take only unit matrix and like no spin orbital effects, or you can use the part as I showed before. Okay, so as I said, the most commonly used is a massive photon-like vertex. What's the problem? So the first part is that I would say correct or without any problems, but the other part includes some derivation that acts on your wave function, and there is coming problem because they generate the D wave contribution of your vector meson. A priori in the Lycon, it's not problem itself because we observe something. But if you will go back to rest frame, this remains generates some D wave contribution, but as I said at the beginning, vector mesons or quarkonia like gypsar or upsilon, we consider like S wave only. So I mean, if we solve in the rest frame their Schrödinger equation, we consider only S like S wave, and so therefore, and also all potential we have on the market we use, we compare, consider also only S wave. No, none of them is giving some D wave contribution. So there is one significant problem of this approach. And moreover, in many wave function, they don't consider Meloy spin rotation. And in our case, when we take only this first term to have only S wave in the rest frame, and when we move to the Lycon, so here we have Meloy spin rotation that generates own contribution to D wave. So actually, if we would use the massive photon vertex and Meloy spin rotation, we have like two sources of the D wave effect in the Lycon. So that's also questionable. So basically, this approach is more postulated than really computed from the first principle. But okay, to compare, we derive a full description for the following four scenarios. So we can take the photon-like vertex plus Meloy spin rotation that we can consider like full theory, because in this case of photon-like only, you don't consider the spin orbital effects. Here, yes. Here again, only pure S waves, so it's only the first term plus Meloy spin rotation. The last two, scenario 3 and 4, we in detail investigate in our previous work. So let's see some numerical comparison on the diffractive data from HERA. So in the top figures, we have scenario 3 dash line and scenario 4. So here clearly the description with the simple S wave vertex plus Meloy spin rotation give best result. The thin and thick line correspond to the, different dipole cross sections, so that give us a little bit uncertainty. And in the bottom we can see the same, but scenario 1 and 2, and here again we can see exactly opposite, that with the Meloy spin rotation that we could consider like full theory, give worse data description than only consider the photon vertex. But if you compare, one could say that you only exchange the dash and solid lines. So indeed, for the 1s states looks like that. But other interesting observable is ratio, for example, psi prime over j psi. Pardon. There we can see again the story is the same. Scenario 3, 4, 1, and 2, but here we can see bigger difference. So if we will try to show the relative impact, so we compare scenario 1 is only photon-like vertex, and scenario 3 is only S-wave vertex, both without Miller spin rotation. The difference is quite significant. In the similar situation, if we consider scenario 2, it's a photon-like vertex and Miller spin rotation. In comparison, simple vertex and Miller spin rotation effect is also quite large. But surprisingly, I would say almost luckily, scenario 1 only photon-like vertex and full S-wave vertex with the Miller spin rotation is close to 0. It means they are very similar to each other. And the effects is large, especially FQ at small q square, is for the reason because the effects is only for transverse polarization. But for large q square, the longitudinal polarization dominates, and it's the same for both options. So therefore, you can see that at a very large q square, they are the same. And in bottom is the same business, but for again psi 2s over j psi. And actually, the same, very similar results you can find also for epsilon over and the ratio epsilon prime over epsilon or epsilon prime 2 primes over epsilon. So at the end, as I said, the problem is that many people use the photon light vertex. That is really difficult to justify at in the details, in the really detailed physics of the quarkonia formation. So we have a problem with the D wave, and especially in most of the wave function, they neglect the spin orbital part. So with combination of the photon-like vertex, we have like double counting of the D wave contribution and so on. So that it's the problem we would like to point out that it should be discussed. But however, the current experimental data are not so detailed to have more numerical comparison about some decision to see some what is really more correct. And of course, we have some uncertainty from different QQ bar potential or other sources of uncertainty. But generally, we expect, for example, from EIC that again the electron production there could be more data with more precision. Okay, thank you for your attention.
Thank you very much, Michal. We have a few minutes questions. Please raise your hand. Any questions for Michal? I don't see any questions or comments, so maybe we should stop here. So let me thank all the speakers of the session. We'll now have a short break and we'll resume our session at 9:55. Thank you, everybody.
Hello, Carlos, Sharka.
Yes. Hello.
Can you hear me?
Yes, we can.
Okay, good. So let's go through the speakers for the next section and test the sharing. Is Thomas connected? Thomas Trula? Yeah. What about Jindrich, Leidrich? No, I'm sorry. I'm sorry. I was going through the poster session. I'm sorry. So we start with Francesco. I'm sorry. Mazaski.
Okay. Hello. Can you hear me?
Yeah. Good. Okay. I'm sorry. Good.
I'm gonna share the slides. Fine. The slides. Can you see them? Sorry.
Yes.
Okay. Fine. Hi. Sorry, I can't hear you.
Can you hear me?
Yeah.
Carlos, your sound is very weak. Maybe you should.
Is it better now?
Yeah, much better.
Okay. Sorry.
Okay. Sorry, can I test the video? One moment. Hello.
Yes, works very well. So I cannot hear Antonio anymore, but we can check.
I think he's muting now.
I don't know if it's intentional or not. Antonio, you're muted.
Oh, I'm sorry. I think I clicked by mistake. Yeah, sorry. So Wei Min.
Yes, can you hear me?
Yes.
I will
Could you
share
try?
my slide.
Yeah,
Yes.
please try to share.
Share. Okay. Then I will share. Oh, there's no PDF sharing. I cannot find it from the.
So when you click share screen.
Yes.
So you should have the PDF file open in the window, and then just choose the window, and then click share.
I cannot find.
You can also share the whole desktop if that's easier.
Can you see the desktop?
Yeah.
Yes, we can see the desktop.
Then I will open my slides.
Yeah, it's fine. Yeah.
How about this?
Yes.
Okay. Great. Do I need to open my video also, or that's all? Oh, that's okay.
As you like.
Okay, great. I will stop sharing.
Okay, thanks. So I go to Changkyang Chua. Please let me know if I spell correctly.
Yeah, I'm here. Now I'm sharing my video. And
yeah, I can see you.
Okay, and I'll try to share my screen.
Okay, I can see the desktop. Can you just try to open the slides?
Is it okay?
Yeah, looks fine. Yeah, thanks a lot.
Good, thank you.
Okay, now we go to Thomas Kadavi. Thomas, are you connected? Yeah, I can see him.
Maybe he has some break, but as I remember, we already tested just before
You
the
tested
start
him?
of the meeting. Yes.
Okay, great. So then we can go to Evgeny Solodov.
Yes, I am here. But I still have this shared screen from Chua.
Yeah. So, could you stop sharing, please? Yeah.
Okay. You would like me to?
Yeah, just share the slides. Yeah.
Okay, let me try. Just a moment. Let me open it. Just a moment, just a moment. Talks. Just a moment.
Okay.
Oh, just a minute. Okay. 217, this one. And yeah, share screen.
Yeah.
Let me try again. Share screen. Here it is.
There you go.
Yeah, you can see it?
Yeah, I can see that. Thanks a lot.
Okay, yeah. So that's great.
Oh, good.
All great.
Thank you.
All works. Thank you.
Okay, thank you.
Maybe can you try to put it to full screen? Extra thing, the slides.
Okay, let me try again. Just unfortunately, I closed it. Just a moment. View and the full screen. This one. Yeah.
Yeah, just
okay.
Just click share again so you can see them.
Oh yeah, inscription. Okay. Where is it?
We cannot see anything, at least me.
Yeah, it's coming.
Now I see it. Yeah,
okay.
Right.
Great, thank you.
Okay. Full screen,
Thank
yes?
you.
Okay, great.
Yeah, perfect, thanks. Okay, so the last one is Guangshan Huang.
Yes. Can you hear me?
Yes.
Okay. I'll try to share.
Okay.
So can you see my slides?
Yeah. So you can just try to have it full screen.
Okay. Yeah, can you see it?
Yeah.
Okay,
that's good.
That's good.
Yes, that's good.
Okay, thank you.
Thanks a lot. Okay. So Carlos, we restart on time, right? So it's 9:55.
And 9:55.
Okay. I'll mute for a second. Carlos, let me ask you. So we'll also stay around for the poster session just after.
No, I can't make that one. At
Okay.
least not entirely. Sorry about that.
Okay. No, don't worry. I just wanted to. So Sharka, it will be only me, or you also cannot connect, right?
Yeah, unfortunately, I have another meeting which I cannot miss. So.
Yeah, no problem. So should I do something in regards of recording or something like that, or it's all covered by the?
I think in principle this is covered by the technical assistants, and they also know what to do. So.
Okay, good. So.
Okay, thanks for staying long.
No, don't worry. So if there is any announcement also.
Just Sharka, will you continue to record or not the video?
Yeah, I continue recording, but for the poster session, I will have to disconnect. So maybe Antonio, if you can record also the poster session, would it be possible?
But yeah, okay. Just we always want to have like two tracks, two recordings in one moment.
Yeah, I'll try that. But it's a backup anyway, right?
Yeah, thanks.
Okay, so we're 1 minute to go. So maybe Francesco can already have his slides ready.
Yes.
Thanks.
Can you see them?
Yes, yes. You are in your office in Torino?
Yes.
By the way, I have an echo. But okay.
Have an echo?
Yeah, but I guess when I mute, it should not be a problem.
Oh yeah.
Yeah, I was saying that because I did my PhD in Torino, so I recognized the style of the office.
Yeah.
Okay, everyone. So we're on time. So I'm Antonio Vidal Pereira. So I'll be chairing this session. We start with Francesco Masaschi. So we talk about investigating the hypernuclear strong interaction with measurements from ALICE. So whenever you're ready, please go ahead. Thank you.
Okay. Can you hear me? Fine. Okay, good morning, everybody. Today I will present you a new precision measurement of the hypertriton lifetime in ALICE that is actually crucial for understanding the hypernucleon strong interaction. So, sorry, 1 second. Let's start with the hypertriton ID. As you probably know, the hypertriton is the lightest known hypernucleus, and it is composed by a neutron, a proton, and a lambda particle. The mass of the hypertriton is around 3 GeV, and as you can see from the right plot, the hypertriton together with all the hypernuclei allow us to extend the nuclear charge to a third dimension, that is the strangeness dimension. And so the hypertriton represents a very powerful tool for understanding the strong interactions beyond the up and down quark sector. Also because lambda hyperons can probe the nuclear structure without being affected by the Pauli principle. In ALICE, we reconstruct the hypertriton exploiting its mesonic charge decay channels. Today we present you the lifetime measurement of the hypertriton in its two-body decay channel, in which the hypertriton decays into an helium 3 and into a pion with an expected branching ratio of 0.25. The other mesonic charge decay channel is the free-body decay channel, in which the hypertriton decays into a deuteron, a proton, and a pion with an expected branching ratio of 0.40. And one of the main reasons why the hypertriton study is so crucial is that we have many hints that lambda hyperons could be produced into the inner core of neutron stars. And so the hypertriton is a unique probe we have on Earth for study and understanding the lambda nucleus interaction. Moreover, the measured lambda separation energy is only 130 keV, and so reasonably the hypertriton could be approximated as a bound state of a deuteron and a lambda, as you can see from the sketch in the right part of the slide. Supporting this theory, this measurement, we have also recent calculations that are based on pionless free body effective field theory that show a large separation between the lambda and the deuteron core. This separation is around 11 Fermi and is in agreement with the measured lambda separation. But which are the consequences of this structure on the lifetime of the hypertriton? And here the point is that we have a very low lambda separation energy. Such a low lambda separation energy implies a small change of the lambda wave function inside the nucleus. And so one could expect the lifetime of the hypertriton to be very close to the one of the free lambda hyperon, that according to the PDG is 263.2 plus minus 2 picoseconds. And here on the right, I reported the collection of all the lifetime measurements that have been done since 70s, 60s, basically. And in particular, the last two measurements are heavy ion collision measurements, the 2018 and the 2019 measurement. And the first one, the 2018 measurement, is a measurement from the STAR collaboration. And this measurement is not in agreement with most of the theoretical models predicting a low lambda separation energy, such the one measured. While the latest measurement published by Alice in 2019 is in agreement within 1 sigma in all of these theoretical models. And all these measurements represent the so-called lifetime puzzle that we want to solve. And I hope I have convinced you that a new precise lifetime measurement is crucial for finally shedding light on the hypertriton lifetime puzzle and consequently on the hypertriton internal structure. And so our measurement is performed exploiting the excellent particle identification of the Alice apparatus. And thanks to the excellent PID of Alice, we are able to identify the hypertriton daughter particles. And in particular, the detectors that are used for this analysis are the inner tracking system of the experiment that is used for the track reconstruction, the reconstruction of the primary and the secondary vertices, and the PID of low momentum particles, the time projection chamber that is used for the tracking and the PID via specific energy loss, the time of flight detector that is used for the particle identification with time of flight, and finally, the V0 detectors that are used for the trigger and for the centrality determination of the collision. And so, as I've already mentioned, today we present you the lifetime measurement of the hypertriton exploiting its two-body decay channel. And the analyzed data sample is the one collected by Alice in 2018 of lead collisions at 5 TeV. And what we are looking for is for an hypertriton candidate that is composed by an helium 3 and into a pion pairs per tracks, with, of course, the related charge conjugates that are close into the phase space and so presumably derives from a common vertex. So what we have performed is the secondary vertex reconstruction, in which we require the matching of helium 3 and pion tracks coming from this common vertex. And as you can see from the right sketch, we have also different topological and kinematic variables that can be used for selecting the hypertriton signal and rejecting the combinatorial background. Finally, our candidates are divided in 9 different CT beams, ranging from 1 to 35 centimeters, and in these CT beams, we will extract the signal. And now we came up to the core of our analysis, that is the hypertriton selection. And for selecting the hypertriton, we have decided to use a machine learning algorithm. In particular, we used a boosted decision trees classifier, a BDT, to discriminate between the signal and the background candidates. A BDT classifier is a supervised learning algorithm, and as all the supervised learning algorithm needs to be trained and tested on a dedicated sample containing labeled signal and background candidates. In our case, the signal candidates are taken from the Monte Carlo, while the background candidates are taken from the like same background. And on the right, you can see the distribution of all the variables that I used for feed our BDT, both for the signal, the red one, and the background classes, the blue one. And what basically a BDT returns is an output, and please note that we perform different trainings for each CT bin. And this BDT output is a score that is related to the candidate probability of being a signal or background. And on the right, I report the score, the score of BDT output distribution of our analysis, both for the signal and the background classes, and both for the training and the test set distribution. And we can see two things. The first one is that we have a very high discrimination power. The second one is that basically the performances between the training and the test set are consistent, and so it means that we are not overfitting our data. And what basically ability does is a reduction of the dimensionality of the selection problem, because rather than put different cuts on the topological and kinematic variables that characterize the hypertriton candidate, here it is required one single selection on the BDT score. And this selection is chosen maximizing the expected selection significance, assuming thermal production for the hypertriton. And finally, candidates that pass the BDT selection are used to fill the invariant mass spectrum that you can see on the right in one CT bin. And in this case, the background component is fitted with a polynomial while the signal is fitted with a Gaussian. And in this way, using a machine learning approach, we are able to extract our signal in 9 CT bins ranging from 1 to 35 centimeters. And correcting our signal extraction, both for the selection efficiency and the absorption in the Alice detector, we are able to, we came up to the corrected CT spectrum that is fitted with an exponential function to obtain the lifetime value from the fit. Lifetime value that result 254 plus minus 15 picosecond of statistical uncertainty plus minus 17 picosecond of systematic uncertainty. And so we have an overall statistical uncertainty around the 6%, while the overall systematic uncertainty is around 6.7%. But how can we interpret this measurement? And so to do that, I put also our new measurement in the collection of the lifetime that I have already shown. And as you can see, we have the most precise measurement available in the market. And the statistical uncertainty that we have obtained is lower than the published world average uncertainty. Moreover, our measurement is also compatible with the former Alice results. But this lifetime measurement basically tells us that model predicting lifetime to be near to the 3 lambda 1 are strongly favored. And so the hypertriton weakly bound nature seems to be confirmed by this measurement. On the contrary, models such the pink one that you can see on the left of this plot, assuming a compact hypertriton seems to be disfavored by our measurement. For example, this pink one is 3.6 sigma far from our measurement. And so, let me conclude saying that Alice has performed a new measurement of the hypertriton lifetime in the two-body decay channel with lead collisions using a machine learning approach for the signal selection. And in this way, we are able to obtain the most precise measurement in the world, and the lifetime value that we obtain confirms that hypertriton is a weakly bound state of a deuteron and a lambda particle. Thanks for your attention.
Thanks a lot, Francesco, for this very nice measurement. I see a question by Marek.
Yeah.
Yes. In a measurement by STAR, they were able to see a 3-body decay where triton decays into pi minus proton and deuteron.
Yes.
Is Alice able to establish the branching ratio between the 2-body and 3-body?
Yeah, this is one of the objectives for the next months, basically, and I also prepared a slide about that. And yes, we in ALICE we aim to extract the first a lifetime measurement of the hypertriton in the three-body decay channel, and also because, as you said, this could provide a first estimate of the 2 to 3 body relative branching ratio. And of course, a three-body decay channel using this approach as a combinatorial, as an enormous combinatorial background, also with respect to the two-body decay channel, but we have also more complexity for feeding our boosted decision trees.
What about the binding energy? How accurately can you measure the binding energy?
Yeah, also the binding energy is ongoing. Also the binding energy, both for the 2 and the 3 body measurement is ongoing.
Thank you.
Okay.
Is there any other question to Francesco? If not, I think again, Francesco, and we could move to the next speaker. Thank you. So the next speaker is Wei-Ming Song.
Hi, I hope you can hear me while I see my screen.
Yeah, both are fine.
Okay,
so Wei-Ming will talk about new observation in charming decays. So Wei-Ming, please start whenever ready. Thank you.
Okay, so the title again is the new observation of the charmonium decays at batch 3, and I'm Wei-Ming Song. I'm from Jilin University in China. So the outline of this talk is that I will give a brief introduction to the topic, and then I will talk about the charmonium decays in the order of psi prime, I mean the psi 2s decays and H sub c decays and the KCG decays. And in the end, it's a summary and look into the future. I want to emphasize that all the observations or all the results are the first observations in my slides, in my talk. And on this slide is a brief introduction to the physics. And I want to tell you that the batch 3 is unique to study the decays of charmonium states. For example, for the psi prime or psi 3686. And as the quantum number of this state is 1 minus minus, and our machine is an electron-positron collider. This means that this state can be produced directly in the electron-positron collision as its quantum number is same as the photon. Actually, we in total have about 450 million events for the psi prime, which enables us to study its decays in very detailed, in very high precision. And another one is for the H sub c. Even though the H sub c could not be produced directly from the electron-positron collision, but as shown by the plot here, the decays or the branch ratio of the psi prime to pi 0 HC is at the level of 10 to the minus 3. As we have a large number of the psi prime, we have a lot of H sub c also, which will enable us to study its decays. And one property of batch 3 is that the pi 0 from the psi prime decays could be fully reconstructed. Then we can reconstruct the full decay chain, and this means that we can study very complicated hadronic decays of the H sub c. Because we can perform PID and full reconstruction, we can have all the decay chain there. And for the KCG, it's similar to the H sub c, but the branch ratio of the psi prime to gamma KCG is much larger. And the radiative photon from the psi prime to gamma KCG is more than 100 MeV, which is detectable also. And the background for the KCG decays in our study is very low. Next slide is my first topic. It's seprem to pp bar phi for the seprem decay. This one is the first observation. And for this three-body decays, we can study the branch ratio and search for the intermediate states in any of the two combination of the final states. For example, to search for the XPP bar in the PP bar environment spectrum. And by studying this decay, and we can test the 12% rule, which is defined by this formula. Is the ratio or the branch ratio of seprem to some hadronic final states to the ICHEP side to some hadronic final states, which equals to the leptonic decays, and it's about 12%. The ratio is 12%. And by the plot here is the environment mass spectrum of K plus K minus. And in this study, the phi will decays to K plus K minus. And we can reconstruct the proton and the antiproton and the K plus K minus. If the environment mass of the K plus K minus is at the position of the phi, then we get the signal of seprem to pp bar phi. By counting or fitting this spectrum, we get the number of events of seprem to pp bar phi. And we have already know the total number of the seprem, and by this ratio, we get the branch ratio of seprem to pp bar phi, which is measured to this value. And then we test the 12% rule, the Q value, as mentioned in the previous slide. It's well consistent with the 12%. It's 11.6%. And by looking at the Dalit plot of the P phi versus P bar phi, we claim that no significant structure there, but there may be some structure. Further study is needed. For the next analysis, is for the observation of the new H sub C hadronic decays, and the spin singlet states, charmonium state H sub C had been observed for a few, maybe 15 years, but its hadronic decays are not well measured. And by studying its hadronic decay, we can test the QCD, and of course, the branch ratios are important for other measurements. For example, studying the pi H sub C spectrum. And we studied 5 decay channels. We listed them in this table, number 1, 2, 3, 4, 5. And the final states are pp pi, 3 pi 0, 5, 3 pions, and 5 pions, 7 pions, and kk pi. And the plot here are the corresponding phase plot for the environment mass of the final state. And for the first 3 ones, pp pi, 3 pions, and 5 pions, we observed the clear H sub C signal. And for the other 2, we set up the upper limit for the branch ratio. And here we come to the KCG decays. For the first one is the KCG to 4 K short, the first observation of this channel. And for this study, it's very important to reconstruct the K short. For the K short reconstruction, we relies on the decay length as shown by the left plot, and the environment mass of the 2 pions from the K short. The signal is very clear, and if we look at the environment mass of the 4 K short, we can see clear KC1, KC0, KC1, and the KC2 signal, and then we get the branch ratio of the KCG to 4 K short as listed in this table. For the next study is the KCG to phi eta. It's similar philosophy. The phi will decay to K plus and K minus, and the eta will decay to 2 photons. And if we fit the environment of the phi KK gamma gamma, we see clear KC0, KC1, and KC2. then we get the branch ratio. And this one is the 3-body decay. We can search for the intermediate states in the final states. For example, for the top 2 plots, it's for Kt0 in phi phi and eta phi spectrum, and Kt1 and Kt2 extra. There's no obvious structure observed. And for the KCG decays to baryon final state, the first one is a KCG to sigma p bar k short. By the similar method, we fit the spectrum of the sigma antiproton and k short. Clear signals are there, Kt0, Kt1, and Kt2. Then we started the Brownton ratio. And again, it's a 3-body decays. We started the intermediate states. And for the Kt0 signal region, we see some hint for the sigma minus 1940 with the significance of 3 sigma. It's evidence for this excited baryon. And in the signal region of the Kt1 and Kt2, there's no clear structure. Then for the psi prime or KCG to another final state in the baryon final state, antiproton K star and lambda. And we can measure the branch ratio and search for the intermediate states. And the top 2 plots are for the KCG decays. We perform a 2D fit. In one dimension is the K star decays to K pi 0. Another dimension is the KCG to P K star lambda. And we get number of events for this decay channel. And for the psi prime to P K star lambda, we perform a 1D fit in the K pi 0 environment, and then we get number of events for psi prime to this final state. As we know the number of events for them, then we can get the branch ratio. And again, we started the intermediate state for the KCG to this final state and the psi prime to this final state by the Dalit plot. There's no clear structure observed. And in the end is a summary. Based on the largest psi prime sample, many decay channels for psi prime, H sub C, and KCG are observed for the first time. And this result for the charmonium decays are crucial for understanding the QCD in the low energy region. And what's more, BEST3 plans to enlarge the psi prime sample by a factor of 3 or more, which means that we will have more results coming in the future. That's all from my side. Thank you.
Thanks a lot for this very nice talk and results. Is there any question to Emmy? It seems always was very clear. If not, we'll then move to the next speaker.
Thank you.
Thank you. Thanks a lot. So move to the next speaker, Chun Kyung. I can see you. Yeah. So Chun Kyung will give a presentation on Correllout bottom bearing to S-wave and P-wave charm baryon non-lepton decays. So whenever you're ready, please start.
Okay, thank you. Oops. Okay. The motivations is LCB found 5 narrow omega C states in 2017. These 5 of them. So far, there are 40 charm baryons observed. However, 16 out of 40 have unspecified quantum numbers. This includes those and the previous 5 omega C states. In addition, there are 2 quantum numbers elements for the lambda C 2940. One is 3½ minus, and the other one is 1½ minus. So those box box states are those with unspecified or ambiguous quantum numbers. Now, the study of bottom baryons to charmed baryons weak decays may shed light on the quantum numbers of some charmed baryons. Up to now, only several color-allowed lambda B to lambda C pseudoscalar decay rates have been measured. These are those 5. We expect we expect more to come. In general, baryon decays are complicated processes. They're difficult to calculate. However, decay processes of B to C transitions with expectating like quarks are simpler. These are bottom baryons. Among them, we see that there is only 4 of them decay weakly, namely lambda B, Xi B, and omega B. They have either 0+ diquark or 1+ diquarks. So we are considering B to C transitions with expectating diquarks. The diquarks here is the bottom baryons. This is the B quark, and then weakly decay to a charm quark, and then form with expectating diquark and form into the charmed baryons. Now, we consider 6 types of transitions. Sorry, this is a rather busy slide. Okay, the first 3 are charmed baryons with S-wave final state. They can be either 1/2 or 3/2 state. They are all parity event. And the second half are all with P-wave charmed baryons. They can also be 1/2 or 3/2, but all with parity odd. Altogether, we consider 17 transitions. And those with star here, okay, those with star are final state that are radiant excited. And those with dagger, the quantum numbers are from Zheng and Jiang. This is working assumptions. Okay, our approach. We use light-front-quark model to calculate these transitions form factors. Light-front-quark models have been widely used in many form factor calculations. We derive all vertex functions, most of them are real, and we extract all form factors. These are the input parameters. We have quark masses, 2 of them, and the other ones, the other one is the diquark masses, and we have this Gaussian width. Okay, one for bottom baryons and one for charmed baryons. Now come to my results. For the first type of transitions, this is the 3/2 plus to 1/2 plus to 1/2 plus anti-triplet transitions. These are our results. And we see that the form factors are close to the expectations from heavy quark symmetry, but not exactly equal. This is reasonable because we use heavy but finite quark masses. And also we have a different Gaussian width, so the overlap integral is not 1. And this is Xi B to Xi C, similar to lambda B to lambda C. This is a radiant state. And we see that the form factors are basically similar but have a sign flip. Now, for the second type of transitions, this is omega B to omega C. Again, our results is a good, reasonable agreement to heavy quark symmetry and using heavy quark symmetry and large NC. And this is for excited, radiant excited charmed baryons. The results are similar to the previous case, but opposite in size. Now is omega B to omega C star. Okay, again, our results reasonably close to the expectation from heavy quark symmetry and large NC. And this is a radiant excited omega C. Now, those are S-wave charmed baryon. Now come to the P-wave charm baryons. Things are rather complicated, but however, result is compatible to the Hadron symmetry, and we can extract the zeta 5 and zeta 6. This is the transitions, the fifth transitions. And again, it's close to the expectation from Hadron symmetry. We can extract sigma 1. This is with the radiant excited final state. And this is the last transitions. Again, the results good comparing to is close to the Hadron symmetry expectations. And we can extract sigma 1. And this is the one with the radiant excited final state. Now, come to the decay rate. Okay, we can compare. We have all type of. This is a pseudoscalar P, K, D, DS, and so on. We can compare these two. Okay, this is a 2940 with a 1/2 minus. This is a 3/2 minus. We see that the 3/2 minus state is basically larger than the 1/2 minus by the factor of 1.5 to 2. This is basically from the kinematics. And again, here is for the final state is charm baryons and the vector, and this is a actual vector. Now they are closer. Okay, our result agree reasonably well with data, and overall speaking, also agree with most of the others' predictions. This is the reference for other predictions. And also compute the up-down symmetry. Okay, here we see that they are pretty much similar for the 2940, and for omega B to omega CP, the alpha are basically positive. Now this is the case for bottom baryon with the vector and actual vector. Okay, compare my result to others' predictions. Overall speaking, my results agree reasonably well with other existing results. Now, come to my conclusions. We study bottom baryon to bottom charm baryons 1/2 plus minus or 3/2 plus minus, and with a meson. The meson can be a pseudoscalar vector or an actual vector. Color allowed decays. All together 6 types of transitions. And form factor calculations are using done by using light from Cobb model. And the right front, the form factors agree well with Hadron symmetry, reasonably well. And rates and asymmetries are predicted close to existing data and result from other works. And predictions can be checked experimentally. And these calculations may shed light on quantum number of some charm baryons, including lambda C 2765, lambda C 2940, omega C, these 3 omega Cs. Thank you.
Thanks a lot for the nice presentation and results. So is there any question to Jin Kiang? So it seems it was very clear. Thanks a lot. We will then move to our next speaker. So our next speaker is Thomas Khadavi. Thomas?
Yes. Hello, everyone. Hope you can hear me.
I can see you, yeah.
Perfect.
Could you share the slides?
Yes, it's right here. So I hope that the connection is fine. I had to run home because the connection at my work was unstable. So I hope everything is okay right now.
Yeah, it is.
Perfect.
Okay, thanks a lot. So Thomas, give a presentation on green functions of chiral currents within OP. So Thomas, please start whenever.
Okay. Yeah, thank you very much. Hello, everyone. Greetings from Prague, Czech Republic. This talk has been done together with Karol Kampf and Jiří Novotný. So I will start the talk with something about green functions. Let me just say that green functions are very important objects in the quantum field theory. For example, for the reason that using them and using the LZ reduction formula, we can calculate some amplitudes of different physical processes, which is of course very valuable thing to do. And in QCD, we are using the green functions, especially we are interested in the 3-point green functions that are made from the interpolating fields. That stands for the external sources in QCD, and these are as follows. So for example, we use the vector and axial vector currents, and also scalar and pseudoscalar densities. In practice, we could have 20 3-point green functions. However, since the QCD is invariant with respect to parity, then the 5 of those 20 green functions are forbidden. So we are left only with these following 15 green functions. I have separated them into 2 groups. The first set consists of 8 green functions that happen to be the order parameters of the chiral symmetry breaking. So it means that they do not have any perturbative contribution. And the second set consists of these 7 3-point green functions that, of course, do have the perturbative contribution. Out of these 15 3-point green functions, we are mainly interested in these 5. And the reason why is that these 5 3-point green functions belong to the so-called odd intrinsic parity sector of QCD. We provided calculations of these green functions in the resonance Square theory at the next leading order with the Lagrangian that you can see right here. It consists of 67 operators and of course the corresponding number of unknown coupling constants. Here you can see that these operators are marked with a symbol of X, which stands either for the single resonance fields, double resonance fields, or triple resonance fields. And of course, whilst deriving this Lagrangian, we have assumed that the saturation of the dynamics is given only by the lightest resonances. So having this Lagrangian, we can, as I said, calculate these green functions. And of course, the remaining problem is that we don't know what value these couplings have. So either we can obtain some decay width or any other observable, and then easily compare it to the PDG value, which we can use to extract some constraint on these couplings. Or we can use, for example, the high energy behavior, which should tell you how the green function should behave at high energies. And whilst knowing this type of behavior, we can use it to determine the value of these couplings. So, for example, let me say something about the canonical VVA green function. The calculation is somewhat straightforward because there are only 6 types of level diagrams in resonance Square theory at the next leading order. And since the VVA green function, its tensor decomposition is given in 4 terms. However, the first out of the 4 terms is the anomaly. So basically, the result that you get is given in terms of 3 scalar functions. And using these functions, the knowledge of these functions, we can construct very important phenomenological form factor WT. The reason why we construct such form factor is that we already know the operator product expansion for the VVA green function, and it tells you that this form factor is of this form. However, it is important to stress out that this VVA, well, it's OPE, is considered only for the case that only 2 out of the 3 momenta are taken to be large. So one of the momentum is soft. So basically, let's just say that we are using at this point so-called 2-point OPE. And while we match these form factors, we give the following predictions. So, for example, this coupling constant should have this value, which can be compared also to the value which you can see right here, that is obtained from the decay of the axial resonance F1. And also another prediction that we can get is the parameter delta BL, which tells you how the Brodsky-Lipage behavior of the pi transition form factor is deviated. So as you can see, our value is slightly of the -1. However, it is in contradiction with the value, which you can see right here, which is slightly of the 0 value, that was obtained from the VVP correlator. So this can be illustrated in a slightly simple way on the following graph. Here you can see the form factor that that is plotted in this graph. And let me start with saying what the Brodsky-Lipage condition tells you. It tells you that if you multiply the q squared with the transition form factor, that if you send the q squared to infinity, then this product should be constant. So if the Brodsky-Lipage behavior is not modified somehow, then you should get this kind of line, which you can see here. This is the dot dashed line, and it tells you that the Brodsky-Lipage behavior is satisfied. However, the Babar, Bell, and Clear collaboration suggests that the BL condition is not satisfied, and the fit using the value obtained from the VVP correlator is slightly off the previous 0 value. However, as I said on the previous slide, our prediction from the VVA green function based on the knowledge of the 2-point OPE for the VVA gives us this black line, which is really off the range of the experimental data. So basically, we know that using the 2-point OPE is not consistent with experiments, which is of course a complication. However, there is no physical argument that would say that the 2-point OPE is the correct one. So we can rule it now. However, there is a way to try to understand it more in more detail. And the way is to calculate the OPE where not only 2 out of 3 momenta are large, but where all the momenta are large. So actual distances, as I said in QCD for a large external momenta, the 3-point green function can be expanded into a asymptotic series of non-perturbative parameters with C-number coefficients. Here you can see the C-number coefficients, so-called the Belsen coefficients, and the non-perturbative parameters are as follows. This is the quark condensate followed by the gluon condensate, quark gluon condensate, and the 4-quark condensate. So let me just show you the contributing condensates and their respective diagrams. So first one, of course, is the very well-known perturbative contribution that in the present is known to several loops. And if I also stress out a canonical example, the VVA green function, it is of course very well known that such a triangle is anomalous. That was found out in the late 60s. And in the forthcoming years, people find out that the triangle is not modified by any QCD radiative corrections at 2 loops. However, at 3 loops, the corrections do not vanish and are proportional to the beta function. The following contribution of the OPE expansion is the quark condensate. It is, of course, very well known for many years because the leading order was studied already in the 94. And the importance of the quark condensate is that it implicates the chiral symmetry breaking. And as I said at the beginning, it contributes to the order parameters of the chiral symmetry breaking. Also, the gluonic corrections to the quark condensate can be studied. It is very important to study such corrections because it gives us an opportunity to explore the renormalization dependence of quark condensates in full QCD. Following contribution is the gluon condensate. Here you can see the set of 6 diagrams that contribute to the 3-point green functions. However, the Bose-summarized diagrams have to be added. So the calculation is, although straightforward, but it's quite lengthy. And the easiest to perform these calculations is in the Fock-Schwinger gauge. Here, let me only mention that since the result must be translation invariant, that these 2 diagrams basically vanish after the translation is taken into account. So we still have to deal with these 4 diagrams. And easiest way, as I said, is to use the Fock-Schwinger gauge. So basically you calculate these diagrams in the coordinate representation. So to obtain the result in the momentum representation, Fourier transform must be applied. And this Fourier transform naturally gives you the contribution of the logarithms. However, although it is a one loop calculation, every logarithmic terms cancel each other at the final stage of your evaluation, which is of course of no surprise because the gluon condensate has a 0 anomalous dimension, so there cannot be any dependence on the renormalization scale. So far I have not talked about quark gluon condensate and the 4-quark condensate, and the reason is that these 2 condensates cannot be evaluated as a standard diagrams, but have to be obtained effectively through a propagation from the non-local condensates. So this is probably the most important slide that I'm showing you here. Here you can see that the non-local quark condensate propagates not only as a local quark condensate, but also as a quark gluon condensate and the 4-quark condensate. And similarly to the case of the non-local quark gluon condensate, it propagates as a local quark gluon and the local 4-quark condensate. Here the functions that give you the coordinate dependence of this conversion from the non-local ones to the local condensates is not trivial, and as far as we know, this is the first time that these results are presented in the literature for all the coordinates of all the respective quantum fields to be non-zero. So this is just a graphical illustration of the previous slide. So you can see the gray blob that basically stands for any vertices that couple the 3 external currents together. And also let me point out that the omitting of the effective propagation of the QCD condensates, as Stefan Harrison says, has been one of the main sources of errors in the existing QCD sum rules, spectral sum rules literature. So this is just an overview of the contributing diagrams to the quark gluon condensate. The diagrams on the right side are probably standard, and everything is clear about them. Here on the left side, we can see how the effective propagation is obtained, because the gluon field here is actually coupled to the fermion line with zero momentum. So using the standard techniques, this diagram couldn't be evaluated because of the pole of the propagator here, but the effective propagation basically saves the day. I'm coming to an end. So the contribution of the foreground condensate, it's probably the most complex one, because the first contribution first set of contributions that you have is the direct contribution, which can be evaluated in the standard perturbative manner. However, the next contributions stem from the propagation of the quark and quark-gluon condensate. And this is, of course, the similar diagram to the previous one that I showed you for the case of the quark-gluon condensate. So once again here, the standard perturbative techniques wouldn't work. So as I said, we have calculated contributions of the QCD condensates up to dimension 6 to the all relevant 3-point green functions in QCD. However, if we try to perform the matching of the contribution of the QCD condensates to the resonance chiral theory, at least for the case of those that belong to the odd intrinsic parity sector of QCD, we still are not sure whether the matching will be successful, because it is somehow complicated. For example, the VVA and AAA green functions are anomalous, so they have the perturbative contribution, which is of course connected to the presence of the logarithmic terms, and it is not easy to deal with these logarithmic terms because, as I said, the contribution of the resonances stem from the tree-level diagrams only. And these tree-level diagrams only do not give you any logarithms, of course. And of course, it's very easy to perform this matching also because of the fact that the resonance chiral theory lacks the canonical power counting. So this is my conclusion. I hope I have said everything I needed to say. So here I'm just leaving you with these conclusion points, and I thank you very much for your attention. And here you can click on this link that will transfer you to the article this talk is based about. So this is everything from my side. Thank you very much.
Okay. Thanks a lot, Thomas, for the nice presentation. Is there any question to Thomas? Okay, if not, thank you, speaker, again.
Okay, thank you very much. Have a good day.
Thank you. So we'll move to the next speaker. So Evgeny Solodov.
Yes, I am here.
Hello, I can see you.
Let me share my screen.
Yes.
Can you hear me and see my slides?
Yes, yes.
Is it okay?
Yeah, it's okay. So Evgeny present on study of resonance states, production in plus-minus integration. So please start whenever you're ready.
Okay. My talk is just kind of overview or study resonance structures in the energy range around 2.25 GeV. This work is triggered by the very nice measurements performed by BESS3, which is BESS measured the plus and minus into K plus K minus cross section and confirms the structure which was previously observed by Babar in this region, but with much higher statistical accuracy. What we do, we follow the same way as it was done in BEST3 data. We fit both experiments together with a resonance Breit-Wigner and coherent non-resonant background. And we confirmed that the resonance structure has about 40 picobarn cross sections. And the parameters are shown here in K plus K minus, it's 22, 27 MeV with very high accuracy. And we are trying to understand what kind of resonances exist in this region more. First of all, in the particle data group, there exists a phi 2170 with relatively close mass and width, and also it was reported in Babar in the cross section for pi plus pi minus. It's very close parameters of the structure exactly in this region. Let's look to the phi 2170 is my slide number 3. This resonance observed in 3 processes, but in only one decay mode. The 3 experiments reported of this resonance: Babar, Bell, BES2, BES3. And all these experiments reported the mass certainly below 2.2 GeV, almost definitely below. And BES3 also concludes that parameter of this resonance in K plus K minus differ from 2170 in 3 sigma in mass and more than 2 sigma in width. Let's look what kind of other structures are observed in this region. First of all, let's look to what has published by Babar. And Babar reported the structures of the region in the eta prime pi plus pi minus, F1 pi plus pi minus, pi plus pi minus, as I mentioned before, and eta pi plus pi minus. First 2, eta prime pi pi and F1 pi pi, are very close to the threshold and relatively wide, and the accuracy, statistical accuracy, very poor. You can look to this observation in my backup slides. But there are 2 very relatively narrow structures observed in pi plus pi minus and eta pi pi. We have fitted these 2 structures in one resonance plus coherent background described by polynomial as before. And we observed the resonance structure with the mass 2270 plus minus 20 MeV and the width around 116 MeV with a 4.6 sigma significance. So this is a raw kind resonance which has a vector kind of quantum numbers. Moreover, we can try to understand if it's the same resonance that observed in K plus K minus. So we fit all 3 cross sections simultaneously with one resonance structure, and we obtained relatively it's a relatively good significance for this fitting, and it could be one resonance which can be raw 2240 with approximately equal branching fraction to all 3 decay modes, and all these resonances are close together. So it's likely that the interference pattern observed in all 3 cross sections are manifestations of the same isovector resonance. Also, we try to understand if we observe omega-like resonance. So we considered also published result by Babar, which reported cross-section from omega pi plus pi minus and omega pi 0, and the sum of these 2 cross-sections also shows some kind of resonance structure. Unfortunately, significance of the structure is relatively small, only 2.6 sigma. The mass and width are very close to that observed in the Church chi plus chi minus mode and eta pi pi and pi plus pi minus. So we try to investigate this region further, and my slide number 7. And of course, if it's a normal two-qubit resonance, it could manifest itself in the k-short, k-long cross-section data. The most precise measurement of this cross-section was performed by Babar, but we stopped this presentation at 2.2 GeV. And the cross-section was already consistent with zero, with the level of 20 picobards. And we decided to extend these measurements up to 2.5 GeV to understand if we could see something similar to the structure observed in K plus, K minus. So in this work, we present these new measurements. And slide number 8 describes some event selections criteria. I'll skip this slide because it's some details can be found in the published paper. I only can say that we consider k-short decaying into pi plus, pi minus. Also, we looking for the high energy photon, which is assumed to be ISR photon. Plus, we also consider k-long candidate as a cluster in nuclear interaction in the calorimetry. Then we perform a kinematic fit, and looking to the high square distribution, we extract data and background, considering signal region in high square and control region in high square. And the distributions of events in these two regions are shown in the slide number 10. On the left, there is a background mass distribution with this in the wider range shown here. We fit it with a polynomial function, and then apply this estimate to the signal region, which is shown on the right. So you see that the signal shown by point with error, and the curve shows the expected background. So we do not see any structure. So we can subtract this estimated background from the signal-like events, and the cross-section is shown on the slide 11. And if we assume that it is the same resonance as observed in K plus, K minus, it should be seen here as shown on the dashed curve. And our data actually excludes this simple picture at the level on 2.3 sigma. But of course, we can try to do the same approach as we did for K plus, K minus. So we can expect coherent non-resonance background. And if we fit our data with a coherent non-resonance background, it's shown in slide 12, we perfectly describe our data. And non-resonance background level is about 7 picobards. But in this fit, it is a relatively strong boundaries for the relative phase of this resonance and non-resonance background. But the picture could be even more complicated. Let's remember that the amplitude of production in plus or minus into K plus, K minus is a contribution of sum of either vector and either scalar amplitudes. But for K short, K long is the difference between either vector and either scalar. And the quark model predicts that either scalar amplitude is 3 times smaller than either vector amplitude. And as we considered earlier, we have actually candidates for this either vector resonance and either scalar resonance here. So we can try to fit with two resonances of both data, K plus, K minus, K short, and long, and we also perfectly describe our new data in K short, K long, and with a non-resonance cross-section about 5 picobards, and this strong boundaries for the interference phase is removing. Even with we can fit it with zero non-resonant cross-section and also obtains acceptable confidence level. It's a high square with a 12 or 14 degrees of freedom. So the two resonances fit allows simultaneously describe the K plus, K minus, and K short, K long data without strong constraints on the interference pattern. But the next what we can try to add the existence of phi 2170 as additional resonance structure, and we fit it with the cross-section hole here, and we inclusion of this phi 2170 does not improve the fit quality, and the fitted value of phi peak cross-section is consistent with 0 and less than 1 picobarns. So it's my summary. Summary is that we have measured the K-short, K-long cross-sections up to 2.5 GeV. The measured cross-section is consistent with 0 with the statistical uncertainties and is at the level of 20 picobarns. The correlated systematic uncertainty in this measurement is about 6 picobarns. The interference patterns seen in the pi plus, pi minus, and eta pi pi data near 225 provides 4.6 evidence for the existence of the isovector resonance, which could be rho 2240. Maths and widths are consistent with that reported by BS3 in K plus, K minus channel. All three cross sections can be fitted simultaneously, and the mass and widths are obtained and shown here. And there is no kind of rho in the particle data group. In particle data group exists rho 2150 with a very poor, very large uncertainty in mass and width. And my summary number 2, the Babar K-short, K-long data do not exclude the existence of this resonance, but strongly restrict the possible range of allowed values of relative phase between the resonance and non-resonance K-short, K-long amplitude. But this restriction can be significantly weakened by inclusion of additional isoscalar resonance with a closed mass. And this isoscalar resonance indication also observed in Babar data in omega pi pi reactions. And all these three, KK, KK, pi pi, and eta pi pi cross sections have been fitted using a model with additional contribution of phi 2170 and no to these final states. So it's still only phi F0 final states. This work already recently published, the references here. Thank you.
Hello? Hello, sorry. Thanks a lot.
Okay?
Yeah, it's fine. Sorry, I just took time to find the unmute button. Thanks a lot for this nice presentation. Is there a question? So I see a hand raised by Gunshan.
Yes.
Go ahead.
Hi, Eugene.
Hello.
Thanks for the talk. Yeah, okay. Could you please go back to the slide of omega pi pi?
Omega pi pi, okay. This one. Oh, no, sorry. Where is it?
I think probably slide 6.
Yes, here it is. Can you see it?
Yes. So do you mean this is combined data from omega pi plus minus and omega pi 0 pi 0?
Exactly.
Okay.
It's a sum of cross sections.
Yeah. Also, do you look at them separately?
Oh, well, it's separately nothing seen, of course. Yeah, it's the same, something very weak. Of course, we look separately, but separately, even here, it's 2.6 sigma. Not really observation, it's just a hint for existence.
Okay. Okay, I see. So since we are also looking at these two channels, so
yeah,
actually
it would be great. It would be great. We are eagerly waiting for the results from BS3.
Okay. Yeah. Okay. Actually, by isospin, there should be a ratio of 2 to 1.
Mm-hmm.
Probably, I guess, since your statistics is very low.
Well, it's a pure quark model predictions, but without any real consideration. It's just very, very simple estimate.
Yeah.
You mean
okay,
here.
thanks.
Mm-hmm.
Okay, thanks a lot. Is there any other question to Evgeny?
Yes.
If not,
Okay.
we thank the speaker again. And
Thanks
we move
a lot.
to...
Thank you.
Thank you. Thank you. And move to Guangsheng, Huang, who will show results on a study of Phi 2170 at DS3. So
okay.
Guangsheng, I can see your slides, so you can start whenever ready.
Yeah, okay.
Thank you.
Okay. So I'm going to talk about the study of Phi 2170 at BAS3. Actually, this topic has already partly covered by Eugene, last speaker. So here is an outline. Since this study is mainly from the stringinium state, so I will give a very short introduction. And for the second part of the machine, I think I will skip. So I will briefly discuss about a few physics channels we have measured. Okay. So the quarkonium states are very good to study the QCD, strong interactions. People are known very well about the charmonium and also plutonium, but the strange quarkonium is less known. Also, there are some XYZ particles observed in the charm sector and the bottom sector. So they should also appear in the strange sector. And also because the mass of the strange quark is in the between, so they should it should be a bridge between light and heavy quarks. So for Phi 2170 covered in this talk, actually it was previously called Y 2175. This was originally observed by Babar and then confirmed by BAS2. And also it was observed by the Bell collaboration. So here is a series paper. You can see it compares with Y 2160. Since the decay pattern is similar, so it is called Y 2175. So now we know it's in PDG, its formal name is Phi 2170. But even though the nature of this state is still not clear. So here you see in the PDG 2018, there are very few channels have been studied. And also from experiment measurement, the width and the mass are distributed very broadly. On the other hand, in series, there are a few models, but not a clear conclusion yet. So we should study them in more detail. So for the machine, I just want to skip since you heard from the previous talks from BAS3. I just want to mention for the Phi 2170 study, we use the data from 2 to 3.08 GeV. That is with a luminosity about 650 inverse peak bar. So here are these data points locations. So actually, as I just mentioned, there are a number of series models. So providing some physics channels we can examine. So the first one I'm going to show is K plus K minus channel. But this is actually already shown by Eugene. So I just showed here the fitting by the three collaboration. Here we give the mass and the width. It's not very consistent with PDG values. Okay, so the second channel I'm going to show that is Phi K plus K minus channel. Since in one series models, the phi 2170, it could be a resonance of phi kk. Here you see this is the model. So we measure the cross sections, and from the line shape, cross-section line shape, we can see here seems resonance, but unfortunately we have only 1 point. From our fit, we can see there could be a peak with a mass just 2.2, around 2.2 GeV. But the width should be very narrow. It could be less than 20 MeV. So it's might be a hint of three-body system of phi kk. And also another mode, you may call it a sub-mode or parent mode, that is a 4-kaon. So here is phi kk as I just showed, and this is a cross-section line shape for 4 kaons. So the behavior is similar. For the both distributions, we can see the outstanding point. That is just at the lambda bar threshold. And also from this lambda bar measurement, we see the abnormal enhancement of the cross-section. So in some theory, it also explained as a lambda bar threshold effect, but might be there also some other explanations. Okay, and here I want to explain something about the phi eta and phi eta prime. So here we can see from theory models, we can examine these two channels. Of course, it could be also tensor quark, as you can see from this figure. But if it's also, it could be a SS bar gluon hybrid. But for this assumption, we would expect a larger decay weight of the phi eta than phi eta prime. Okay, so we have measured the phi eta from phi to kk and eta prime goes to gamma pi pi. So here you can see we have very nice signal. So here, this is a cross-section line shape. So we get the mass and the width, and we plot the this mass versus width in this plot. Okay. We are also measuring the phi eta process, but the result not finalized yet. So here we use a bar result that's published earlier. So from these two widths, we can get the ratio. This is a small number. So as I just showed, if it is a SS bar gluon hybrid, the ratio should be a much larger number. So from this result, we seems like it cannot be a SS bar gluon hybrid. Okay, but on the other hand, if you take into account the eta prime mixing, something might different. So it could be a resonant decay. For example, if you examine the gypsy decay, the eta prime rho should have a smaller decay weight than rho eta. That is due to the mixing. However, if you examine the phi 2170 case, here is an archival paper just posted 2 days ago. So they examined this ratio, and their conclusion that is if you consider the eta prime mixing, this could be explained as either this should be SS bar. It could be either a SS bar or SS bar gluon hybrid. Okay, and the last channel I want to show, that is KK pi pi. This should be a very important channel. From actually from this plot you can see. Also from the intermediate state, you can examine a few channels, physics channels. But previously only Babar has some data for these states. Also, BAS2 previously using ICHEP have some preliminary results, but only with upper limit. So at BAS3, we examine the K plus, K minus, pi 0 or pi 0. Since we have good statistics, we do a partial wave analysis at some high statistical energies. So here you see the components of each of these process. So here we don't see the K star 1400, but we try to measure the Born cross-section for the KK pi pi and also the submode. And we performed a simultaneous fit of these submodes. So the conclusion is that for this one and this one, it seems like we have the decay pattern for the 52170, but for these two, there seems not, since the significance is very small. But for these two, the significance is close to 5 sigma. So from the fitting result, we can also have the mass and the width plot here. Okay, so that's basically I want to show here. Finally, is overall picture of the 52170 mass and width. And we hope this new measurement could give some more knowledge on the 52170. Okay, so finally is a summary. So I would like to say the stringent states are relatively a new field and should to be explored. And although BAS3 provides some new information for the 570, but it is still not enough to distinguish from these series models. So that means the more studies are needed. But actually, I can tell you that there are quite a few analyses on this topic are going on at BAS3. And on the other hand, we also hope series could have reviewed this topic and give some input. Okay, thank you.
Thanks a lot. It was very interesting measurements and presentation. Is there any question to Wangsheng? It seems it was all very clear. Thanks a lot again. So we come to, thank you. We come to a close of this block. And thanks again to all the speakers. And we go to the coffee break and reconvene at 11:35. Thanks to everyone. Hello, Carlos.
May I test the translation?
Hello, Alexei. Yeah. Hello.
Okay.
Yeah, I can see you. Let's just check if Carlos wants to go through the test. If not, we can just.
Yes. Hello, Antonio. I can maybe. Yes, if the following speakers are online, we can check the screen sharing quickly. Maybe start with Marian. If you can share your screen just to see that's working. Marian, are you online? Okay, let's move to Isabella. if you can share your screen. Maybe everyone really went for coffee. Well, Alexei, maybe you can share your screen. Yes, we can see it well. Maybe you can go full screen and then check you can move your slides forward. Yep, very well, perfect. So then, Veronica, are you connected?
Yes, I'm here.
Yes, please try to share your screen.
Yes.
Alexei, maybe you need to stop sharing yours
Yeah.
first. Okay, good. Go ahead, Veronica.
Okay, I think that
Very good.
you can see.
Yes, we can see the desktop. Maybe you can try go full screen.
I think that there is, okay.
Yeah, that should be good enough, I think.
I think F5 is like really full screen. Try to press.
Yes, because I don't use Acroread.
I think you need to go on the menu on the button which has a little bit the three
in this
lines
way
on the.
you can see.
Yeah, we can see that
okay,
way. Just
okay,
yeah, that.
okay. Yeah,
There is the button next to the one with the three horizontal lines on the top bar. I think that one.
Yes, but is another program to see the PDF file, so it's a little bit different.
Yeah, like that is good. I mean,
Okay,
it's big enough. Okay.
This work, okay.
yeah, no problem. Okay,
Okay.
so let's now try Runki Ma.
Yeah, I'm here. Okay.
Okay.
Oh, can you see it?
Yes, very good.
Oh no.
You wanna also go full screen?
Oh no, maybe I need to use another software. Okay. Oh. Oh no. Please hold on. Yeah, it's this one. Oh, can you see it?
Yes. Just
Okay.
move to the next slide to make sure. Yeah, very good.
Yeah. Okay.
Excellent. So then, Ralph, can you try yourself to?
Okay, I will do.
Very good. Wait.
That's not me, actually. Someone
Yeah, exactly. Yeah, I was confused. So yeah, Marian, we wanted to try before. Now he's here, so very good. That's working. Marian, can you hear us? We cannot hear you. Maybe you're muted.
Hello, sorry, I'm Isabella.
Okay.
Yes, my microphone, I had some problem with my microphone. Now I solved it.
Okay, but now the person who is sharing is Marian, right? Who is muted. But Marian, if you can try to unmute, and in any case, we can see your slide, but we need to also hear you. Okay,
Hi, can you hear me?
We can hear you now, yes, but now we lost the slides. Maybe.
Okay, I can try it once again.
Let's try both at the same time.
Okay, it should be there, and I will try to start the video. Can you also see me?
Yeah, perfect.
Okay.
Everything
okay,
works.
Great.
So let's go then to Isabella now.
Yes, I'm here. I tried to share.
Very good. Yes, perfect.
Okay.
So then let's come back to Ralph.
Okay, I think you should see my screen.
Yes, very good.
Somehow, wait. Okay, that's moving. I think you see also the changes, right?
Yeah, now it's moving, yeah.
Oops, what's going on here?
It's an empty table. I don't know if that's supposed to be
Yeah,
like that.
that's not supposed to be like that. Let me try this differently. Maybe try this. Okay, wait a minute. Okay, let me try with the PowerPoint if that works better. Where's it? It's not there. It's really funny. Okay, I think this is somehow related to my computer. It doesn't really see things properly here.
Okay, we can see the screen again. Yeah, the table is still empty. Okay, well, you have some time to figure it out.
Yeah,
I mean,
I'll fix that. Yeah, eventually, hopefully. Okay.
Okay, very good. And then last speaker, Giacomo. Can you please try to share your screen? If you're there. Maybe not. Or if you're speaking, you're muted. We cannot hear you. Okay, maybe he stepped away for coffee. So, okay, we are, I think, ready. We still have 4 minutes before we start. So we are about to
Hello?
start. Maybe we can start. You can start sharing your screen, Marian.
Yes, okay, I'm here. Give me a second. Okay, I will try to start the video.
Very good. We'll wait a few more seconds and then you can start.
Great. Okay, so can I start?
Yes, so welcome back everybody to the last part of the strong interaction and hadron physics session. So we'll start with a presentation by Marian. Please go ahead.
So good morning, everyone. I will be talking about the ordered parameters of this spontaneously broken chiral symmetry in low energy QCD. This will be partly an overview of available results, and then I will also present some our results, which however are not by any means conclusive. So the main point of this talk will be that to call into attention that that these ordered parameters are still not very well known, and there is a big uncertainty in their values. But first, let me start by a few more introductory slides, so the talk would be hopefully more palatable to a wider audience. So as we know, quantum chromodynamics is the theory of strong interactions. There are 6 flavors of quarks in 3 colors, and the principle of Floger gauge invariance gives us the gluons. And what happens at low energy, as is well known, the gluon self-interactions cause the Complex constant to grow, and the usual quantum field theory perturbative expansions fail. So this means the quarks and gluons are not the appropriate degrees of freedom at low energies, and the quark confinement in the Hunter spectrum is born. So what can help us to evaluate this low energy region is the approximate symmetries of QCD. So if you look at the QCD Lagrangian, we can see that the quark flavors differ only at their masses. So if we assume that the U and D, the light quark mass is approximately the same, that the SU2 symmetry group is born, the isospin symmetry. If we assume that also the S quark mass doesn't differ by much, the SU3 symmetry group is born, and which is called the L-fold way. And if we also assume that the light quark masses are approximately 0 or very small, then the chiral symmetry is born, the SU-L times SU-R 2 or 3 group. So, however, parity doublets are not observed in the spectrum. So this is strong evidence that this chiral symmetry is actually spontaneously broken. So an effective theory of QCD at lower energies can be constructed by using these symmetries, the so-called chiral perturbation theory, where the relevant degrees of freedom are the pseudoscalar mesons and not the quarks or gluons. So these are the goldstone bosons of spontaneously broken chiral symmetry. The Lagrangian is then constructed as the most general form of which respects these symmetries and is organized and its expansion in derivatives and quark masses. So in the 2-flavor case, which describes the pions only, the range of validities of this theory is up to the Kn mass. And if in the 3-flavor case, where we get the pions, Kns, and eta, the range of validity is up to the vector mesons, which the lowest one is the rho meson at 770 MeV. So these are the building blocks of the theory, the pseudoscalar mesons, and based on the transformational properties, the power counting can be evaluated, and the Lagrangian can be constructed. So let's have a look at the Lagrangian in the 2-flavor case. So we can see that the lowest order there are two low energy constants, F and B, which is the pion decay constant in the chiral limit and the quark condensate in the chiral limit. And these two constants is what I will, for the purpose of this talk, call the order parameters of the chiral symmetry. So the lowest order constants. At the next to leading order, there are 7 more constants and several dozens in the next to leading order. So as can be seen, to this theory to have a predictive power, some information is needed to fix these LECs, even either from phenomenology or from first principles or calculation from lattice, for example, which is the most precise way nowadays. So in the three-flavor case, we get once again two order parameters at the lowest order: the pseudoscalar decay constant in the chiral limit and the chiral condensate. At the next to leading order, there are 10 more constants and about 100 in the next to leading order. So let's have a look for a moment at the quark masses, so which are also free parameters of the theory, but these are nowadays pretty well known from lattice calculations. What I present here, and I will present quite often in this talk, is the data which are evaluated by the flavor lattice averaging group. This is a group which evaluates various lattice calculations, and for our phenomenologists gives an assessment of the quality and gives them some averages. So the light quark masses are very well known. This is the average of the U and T quarks. The strange quark mass is also quite well known nowadays. This is the ratio of the strange quark and the light quark masses, and even the isospin violating parameter R is now pretty well known from lattice. So let's look at the order parameters in the two-flavor case. So I will now introduce parameters Z and X. These Z and X are conveniently normalized order parameters, so it will be easy to understand the value. So in this form, in this normalization, the values of Z and X can be between 0 and 1. Which means that, for example, if these parameters were close to 1, that would mean that the pseudoscalar decay constant or the chiral condensate are close to their maximum value, and that would mean that the lowest order in the expansion is dominating the theory, so the theory then converges well and works well. If Z would be close to 0, that would mean actually that the chiral symmetry is getting restored and the confinement is getting broken, which obviously is not the case. If X would be close to 0, that would mean that the scenario with a small chiral condensate would occur. So let's have a look at the two flavor values from lattice and some from phenomenology also, and we can see at a glance that the values are pretty close to 1. So what we can see that in the two flavor case, which describes the pions, the theory works very well, and the lowest order dominates the theory, the expansion. So let's now have a look at the three flavor case, and once again we have the Z and X, which are between 0 and 1, but in this case these are the three flavor parameters. And immediately we can see that the situation is more complicated. I will go into a bit more detail in these various evaluations. So the most recent phenomenological next to leading order chiral perturbation theory result by Binance and Ecker from 2014. They have two various fits, the main fit and the free fit, which differ in some assumption about large NC behavior, which I will not go into in detail. But we can see that their values are a bit different. They don't give us any error bars, but we can maybe a theoretical error can be evaluated by the difference of these values. In any case, these are much smaller than 1. We can see that the order next to leading order PT was closer to 1, at least in the case of the pseudoscalar decay constant and the chiral limit, but the newer values are smaller. If you look at lattice, and this is quite important, the flag actually doesn't give us any newer value than from about 10 years ago, which is unfortunate. So in this case, in contrast to the two flavor case, we don't have any reliable recent, at least according to the flag, recent computation from the lattice. There are some now also a few result calculation which combine lattice and some theoretical formalism like horizontal KPT here and large NC here, which produce some values. and which, as you can see, differ quite a lot. So there are two main points from this evaluation which I would like to say. The first point is this, as we can see, the various results are pretty incompatible with each other. So there's a big uncertainty in the values of these constants. And the second main point here is that quite possibly the values of these order parameters is much lower than 1 in this normalized case, or in other words, that the leading order in the expansion might not very well be dominant. So what we try to add into this discussion is the observables from the eta to 3 pi decays. So the decay to eta to 3 pi were not used in any of these evaluations. So we calculated in the so-called Risson-KPT framework. We choose the decay width in the charge channel and the neutral channel, and also the Dalitz plot parameter A. We also evaluated the higher slopes, higher Dalitz slopes, but we found that they're not well predicted or not reliably predicted from theory. So we used to use these 3 parameters, which are very well known for experiments. So there is the experimental error is very small. So what we did is that we actually used the Bayesian framework based on the Bayesian theorem, where we calculated the probability density of these parameters being true given this data. And the input was the experimental distributions, which we can see here, of these observables, and some theoretical assumptions about these parameters. So what we did this numerically in some form of Monte Carlo sampling, and this can be understood as generating a very large ensemble of theoretical predictions, which are then compared with the data. So let me show the results here. This plot shows the probability distribution, the probability density of X and Z, which are between 0 and 1, and in 1 sigma, 2 sigma, 3 sigma contours. And what is overlaid here are the various other results which are presented earlier. And as you can see, we were not able to pin down very precisely the value of these order parameters, but also one can see that we are at about 2 sigma compatible with almost every other. So there is not some contradiction here, or we cannot exclude any of these other determinations, but we do get some preference for a higher ratio of these parameters X and Z. So if we introduce a parameter Y, then we get around 1.5 the preferred value with some significant error or uncertainty here. So we also tried to add pi scattering into the analysis. In the same, we actually reproduced the analysis done by Stern and collaborators in 2003, using the subthreshold parameters of the pi scattering, which was based on a pretty old data from Brookhaven National Laboratory. And what can be seen here, what we actually found that the pi scattering data prefer low values for this ratio of parameters Y. Okay, we did more, but this is the most simple result. And if I remind you, the ATO2 data seemingly prefers values are 1.5, while this prefers a very low values. Now there is a pretty big uncertainty here because the data have a pretty big uncertainty here, in this case of the parameter alpha. So, however, of course, there are more recent, more precise data from the NR48 available. So this is what we are working on now to actually try to pin down this value from pi scattering, and it will be interesting to see whether if this average value of alpha holds about 1.4 with a smaller error, then would mean that a very low value for this parameter Y, and actually the chiral condensation should then be very small, which would be in contradiction with other evaluations. So it will be interesting to see what will happen. So let's, instead of a conclusion, let me put a bit more context into the discussion by pointing to that this is connected with the phase structure of QCD with varying number of light quark flavors. So as is now very well known for a long time, the familiar quark confinement, the chiral symmetry breaking, and the Hadron spectrum is only present in QCD for a low value of quite light quark flavors. So there is a critical value of quark flavors where the chiral phase transition occurs, and then the chiral symmetry is restored. There is a conformal window for a very large value of light quark flavors. Even the asymptotic freedom is lost. So this can be interpreted as some counterplay between the condensating effect of gluing self-interactions and the screening of light quark loop vacuum fluctuation. So what is predicted is a so-called paramagnetic inequality, a dependence of the light quark flavors, and one then expect that with the rising number of light quark flavors, all the parameters should be suppressed. So it's not surprising that the 3 flavor parameters should be smaller or suppressed compared to the 2 flavor ones. Of course, the critical value is much higher than 3, right? What I have seen are the latest calculations show about values between 7 and 10 or so. But it would be not completely excluded or not surprising if there was some suppression already between 2 and 3. So this was actually proposed 20 years ago by Stern and collaborators, and what 20 years later, as we can see, the issue is still not solved. So the question is whether there is a difference between the SU2 and SU3 theory, and we still don't know that by certainty. Okay, and what we have seen that this is quite some serious possibility. So thank you very much for your attention.
Thank you very much, Mary. We're already out of time, but if there's any quick urgent question, please raise your hand. If not, let's thank the speaker again and move to Isabella Grazia, who will be telling us on light meson decays at BESS 3.
Yeah. Okay, you should be able
see your
to
screen.
See.
Yeah, very good.
Okay, perfect. So in the following slide, I'm going to show you the latest results on light meson decay at BESS 3. This is a particular important physics that can be assessed in BESS 3 because allow to understand the low energy QCD, in particular the eta and the eta prime physics, and can also be used for test the prediction of a chiral perturbation theory to probe the mass difference between the up and the down quark, but not only, also useful for search and test for test fundamental symmetries and for search the physics beyond the standard model. Of course, the time is not enough to show you all the analysis that are ongoing and that was done, but I try to summarize on the table here on the left, some of the most important analysis for the eta and the eta prime. Some of them are already published. You can find also more analysis that was done on these topics in the backup slides. And there are still a lot of analysis that are still ongoing. So new results will be also ready soon. Instead, on the table on the right, you can see what we are going to talk about. So the 4 analyses that I choose for this conference: eta prime 3, eta prime analysis, and the analysis of the Dalitz plot of the omega decay into pi plus pi minus pi 0. So the BESS 3 detector was already introduced. Here you can see a picture of the laboratory, which is in Beijing, a top picture, and there is a recent upgrade on the beam energy of electron and positrons that allow to reach the energy of 2.45 GeV. So, and the BESS 3 detector is located in the hole that is here pointed by this arrow, and more detail also about the detector can be found in the backup slide if you are curious and interested. The data sets that we used for the analysis that I'm going to show is based on data collected in 2009 and 2012 on the GEPSI invariant mass, which correspond to a sample of 1,300 million of GEPSI data. But take in mind that in the last 2 years, we collect a total, in total 10 billion of GEPSI data. So we have more data that could be useful for future analysis. And on the plots, on the plot on the right, instead, you can see the decay, GEPSI decay that we used to select a pure sample of eta prime and omega with the relative branching function. So this is why the GEPSI decay allow to us to study with a very high precision the decay, the light meson decay. So my first analysis that I'm going to present is the precision measurement of the branching fraction for 5 different eta prime decay modes. This is the first measurement of absolute branching fraction because due to the difficulty of tagging the inclusive eta prime decays. In this case, in this analysis, we use the gamma conversion to E plus E minus annihilation to tag the eta prime. This allows to improve the resolution of a factor 3 for the radiative photons. And the picture that you can see on the left show the distances between the point, the conversion point, and the interaction point. The 2 rings are the structure related to the beam pipe and the inner wall of the MDC. So we can apply a cut requiring that these distances should be larger of 2 centimeters in the transverse plane in order to suppress most of the background and so to have a very clean sample of tagged eta prime. Then we can reconstruct exclusively the eta prime decay into the 5 decay modes. You can see the invariant mass distributions of the decay that we are going to study here. And in this case, in order to increase the statistics, we require that the photons is directly detected in the calorimeter. So this allows to have more statistics. And finally, we fit the invariant mass distributions in order to extract the signal yields, and then we can calculate the branching functions following the formula reported here. The results are summarized in the table that you can see here. This column is related to the measurements at the strip. And the comparison with what was reported in the particle data book. There is a very good agreement between the measurements. Also with CLIO-C, we are in agreement within 2 standard deviations. And we also obtain a measurement of the branching fraction for the radiative decay of GEPSI into gamma eta prime, which agree with what was reported in the PDG with a very improved precision. Going to the next analysis, we also search for the rate decay of eta prime into 4π0. This decay mode is suppressed because due to the S-wave CP violation, but higher order contributions involving, for example, D-wave pion loop, show it here, or the production of 2 F2 tensor mesons in this second case can be allowed without violation, without the CP violation. And there is a theoretical prediction, which is based on the carrier perturbation theory and the VMD model that estimate that the branching fraction should be of the order of 10 to the minus 8. So this is why we are looking for these rare decay modes. This is a pure neutral channel, so we don't have any charge tracks, and we apply the energy and momentum conservation and the mass constraint for each pi 0, and the plot that is shown here reports the chi-square distribution for the 8 C-fit. And in particular, we can see the region at the lower chi-square, which is the signal region. Here is the dotted line in red is for signal simulation, and the distribution for data and all the backgrounds that are taken into account for in this analysis. After the selection of the cut on the chi-square, that should be lower for 30 in order to select the signal, we have a look to the invariant mass distribution of the 4 pi 0. Here you can see the invariant mass. The signal region is between 0.9 and 1 GeV in the invariant mass, and as we can see, we don't see any significant eta prime signal. The background, the broad structure below 0.9 is very well understood and described, and is coming from a peaky background of eta prime decay into pi 0 eta. So since we don't have any significant signal, we calculate an upper limit at 90% confidence level, and we found that the branching function should be lower of 4.94 times 10 to the minus 5. So we are still far from the prediction of 10 to the minus 8, but we improve by a factor 6 the previous most stringent results. So in this case, maybe with the new data sets can also allow to improve this upper limit. Another important analysis published recently is the search for the doubly radiative decay of eta prime into gamma gamma eta. The radiative decay, the doubly radiative decay of gamma gamma pi 0 was already published by BESS3, and the non-resonant contribution to the branching function is also extracted, and it is in agreement with the theoretical prediction. For the eta prime decay into gamma gamma eta, instead there is no measurements. In literature, there is an upper limit from GAMS 4-pi collaboration, which set the branching function, the upper limit, to be lower of 8 times 10 to the minus 4 and 19% confidence level. Also, in this case, theoretical prediction based on a BDM model and a linear sigma model predicts branching function of the order of 2 times 10 to the minus 4. So this is why we are searching for this decay. So, and the last plot here show the invariant mass distribution of gamma gamma eta, where we can see a very small signal around in correspondence of the eta prime invariant mass, but with a very low significance of 2.6 standard deviation. So we extract the upper limit at 19% confidence level, and this upper limit should be lower than 1.33 times 10 to the minus 4, which is below the prediction, the theoretical prediction. So there is still a little bit of tension between the measurement and the prediction. Also, in this case, more data and the same analysis with the full ICHEP data sets is useful to better understand what is going on. Finally, the last analysis that I want to talk about is a Dalitz plot analysis for the omega decay into pi plus pi minus pi 0. It is important not only because it allows to better understand this decay, which contributes, is one of the most higher contributions on the anomalous magnetic moment for the muons, but it provides also more constraints for the calculation of the electromagnetic form factor for the omega decay into pi 0 gamma star. can also be useful for testing the prediction of Dalitz plot distributions in a dispersing framework, and also to estimate the cross-channel effect. This effect is related to the fact that the omega decay, this decay goes to the omega pi, and the pi, the third pion could interact with the decay product of the omega, and this is what we call the cross-channel effect. A very clean sample of omega events was selecting using Gibbs decay into omega eta, where the eta is reconstructed into 2 photons. And the plot on the right show the Dalitz plot distribution on the y and the x, which are 2-dimensionless variables shown here, where U, T, and S are the squared invariant mass combination of 2 pions. It is more useful to use the polar coordinates, which are defined as a function of the x and the y, because the density of the Dalitz plot, which is this function modulo of m squared, can be written in this way, where f is a function that can be parameterized as a function of the polar coordinate z and phi. So
Isabella, you're running out of time. If you can try to wrap it up,
yes. Please. So we fit the data in order to extract the parameter from this function. And here are the results. What we can see from these results is that the Dalitz plot differs from a pure P-wave phase space factor, which is the case in which we don't have a final state interaction, and is instead in good agreement with the theoretical prediction in which the cross-channel effect are not taken into account. So this is my conclusions. So I show you that the Gibbs decay provides an excellent laboratory for study line meson decay. We also already tell us that we have 10 billion of Gibbs data, which can be useful for more analysis on this topic, with more interesting results are expected in the near futures. So that's all from my side.
Thank you very much, Isabella.
Welcome.
Are there any questions for our speaker? Okay, I don't see any. Thank you very much again, Isabella. We'll move to our next speaker, Alexei. You can go ahead and try to share your screen again. Very good. You can start whenever you're ready. Alexei, we don't hear you. You're muted.
Yes.
Okay.
Okay.
Very good. Yes, we can see the screen and we can hear you. Go ahead.
This talk is devoted to a review of recent result of annihilation of E plus E minus pairs into Hadron in SND experiment. The main part of SND non-magnetic detectors is free-lies calorimeters, a track system, and Cherenkov counter are located in the center of the detector. A muon system is located outside of the detector. The main physics program of a SND experiment is the study of all process of annihilation of an E plus E minus pi into hadrons up to energy of 2 GeV in the center of mass system. Measurement of total cross-section for annihilation of E plus E minus pairs into hadrons, also a study of the dynamics of studied process. The collection of statistics of complex Web 2000 began in 2010. In 2015, the modernization of complex was started. to transfer it to a new ejection complex. In 2016, the collection of statistics was continued. During the operation of complex, about 320 reserve peak bands was collected. This slide shows the depends of accumulated luminosity integral on the beam energy. The maximum of luminosity integral allocated near masses of light vector mesons, F1 mesons, and nucleon anti-nucleon parts production threshold. This report will present result of studying the process Laplacian minus into pi plus pi minus neutron anti-neutron pi 0 eta gamma e plus e minus into f1 mesons and e plus e minus into 3 pions. Experimental studies include measurement of a cross-section of the E plus E minus annihilation process into hadrons. These measurements are largely motivated by the need for high precision calculation of the hadronic contribution to the anomalous magnetic moment of the muon. In particular, the E plus E minus into pi plus pi minus cross-section in the energy region below 1 GeV gives a dominant contribution to this value and should be measurement with accuracy better than 1%. In this log, the cross-section of measured process is measured with an accuracy of better than 1%. The rho and omega measured parameters are agreement with previous SND experiment. This slide showed a comparison of the result of this work with previous experiments. This work, the picture shows the relative difference between the measurement cross-section and the approximation function as a function of energy. The shaded area corresponds to the squared sum of systematic statistic SND errors. In the energy region from 600 to 700 MeV, there is a 3% deviation from BABA data and significant discrepancy with lower data. The new experiment is on E plus E minus to neutron anti-neutron is based on 27 data set and uses a different method. Calorimeter trigger time distribution is analyzed. The time distribution fitted by some distribution for signal, cosmic background, beam background, and E plus E minus annihilation background. Our result is lower than the previous SND experiments measurements. The reasons are underestimate the beam background and incorrected MC simulation. The E plus E minus into neutron and anti-neutron cross-section dependent on 2 form factors. The ratio of form factors can be determined from the analysis of the cosinus theta distribution. Cosinus theta distribution is well described by 1 plus cosinus square theta. Dominate of the GM terms in cross-section is described. For process E plus E minus to eta pi 0 gamma. The process E plus E minus pi 0 in eta pi 0 about 1 day is studied for the first time. The 5-photon final state is used. The signification contribution of omega eta intermediate state, which is seen as a peak in the pi 0 gamma distribution mass. The background contribution is estimated from kinematic fit chi-square distribution. The non-omega eta signal is observed with wide eta pi 0 mass distribution. It may arise from the process E plus E minus into a 0 gamma or and or also A2 0 A2 gamma. We show it E plus E minus into omega eta cross section is in a good agreement with SND and KMD free measurement in the omega into 3 pines decay's model. The non-VP E plus E minus into eta pi 0 gamma process is observed with significance of 5.8 sigma. We perform the first measurement of the cross-section of this process in the energy range from 1 to 2 GeV. The predicted branching fraction F1 into E plus E minus corresponds to the one production cross-section from 30 to 70 nanobarons. The decay's model F1 into eta 2 pi 0 into 6 gamma is used. This final state is not produced in single photon annihilation. The main background source are E plus E minus into omega pi 0 into 2 pi 0 gamma and eta gamma and omega 2 pi 0. After this slide background, after applying selection criteria, 2 events have been observed at peak of the F1 resonance and 0 events beyond the resonance. The significance of Hadron signal is 2.5 sigma. Results of E plus E minus into 3 pions. Both SND experiments are consistent with each other and with the Baba measurement. 2 peaks in the cross-section correspond to the omega 20 and omega 48 resonance. Systematical uncertainty on cross-section is 4.4%. We analyzed the two-dimensional distribution of charged pions momenta and the pi plus, pi minus mass spectrum. The distribution are fitted with a model including the rho 770 pi, rho 1450 pi, and omega pi 0 intermediate state. A significant fraction of rho 1450 pi intermediate state is observed in the energy region from the 1.55 to 1.75 GeV. The cross section for intermediate state rho 1450 pi differ significantly from 0 in the range from 1.55 to 1.75 GeVs, where the resonance rho 1680 is located. In the rho 770 pi cross section, the resonance structure near 1680 MEF is not seen. We concluded that the rho 1450 pi intermediate state gives a significant contribution to decrease omega 1680 into 3 pions, and that the omega 1420 into 3 pions decrease is dominated by rho 770 pi intermediate state. In conclusion, I can tell what the S&T detected accumulated 320 reverse picobarn of integrated luminosity in the energy range from 0.3 to 2 GeV. The A plus A minus into P plus P minus cross section has been measured with a systematic uncertainty better than 1%. The accuracy of A plus A minus into neutron ion neutron measurement has been significantly improved. Radiative process A plus A minus into eta pi 0 gamma has been measurement in the energy range from 1 to 2 GeV. The first indication of process A plus A minus into F1 1285 has been obtained. The dynamic of process A plus A minus to pi plus pi minus pi noise has been studied in the energy range 1.15 to 2 GeV. Thanks for attention.
Thank you very much, Alexei. There is one question by Marek. Please go ahead.
It's a comment that this result, the new result on E plus E minus going to neutron, anti-neutron at threshold is actually very useful, because Fenice initially suggested that near threshold, the neutron, anti-neutron production cross-section was larger than proton, anti-proton, which gave rise to all sorts of crazy speculations, including a paper that I wrote. So it's reassuring that things are back to normal. Just as expected, the neutron cross-section near threshold goes down, as it should. Sanity is restored. Thank you.
Thank you.
Thank you very much. So, are there any questions or comments for Alexei? Okay, if not, let's move to our next. Thank you, Alexei, again. Let's move to our next presentation by Veronica Di Leo, who will be telling us about Chloe and Chloe too. Go ahead.
Okay. Can you see the talk?
Yes, very good.
Okay, so the topic of my talk is the results and perspectives on hadron physics at Chloe 2. I'll show you the Frascati factor in the Chloe 2 detector. I report the final results on the E-time per plus per ounce decay, the status on the E-type 0 gamma-gamma decay in the boson search, and also the progresses on the gamma-gamma studies. Okay, here you can see a sketch of the Frascati factory, where is visible the Linac accelerator, the BTF facility, and then the Daphne complex. Daphne is a double ring collider of electrons and positrons that work at the center of mass energy corresponding to the field meson mass. In 2008, to increase the number of collisions, the Crab-West collision scheme has been implemented together with a large beam cross angle. In the right part, instead, you can see a cross-section of the Chloe detector in the YZ plane. It consists essentially of a huge cylindrical drift chamber that is surrounded by the lead scintillator fiber calorimeter, and all the detectors are immersed in an axial magnetic field of 0.52 Tesla. In 2013, the Chloe detector undergone several upgrades. The upgrades includes the inner trigger that is here represented, to improve the vertex reconstruction near the interaction point, 2 new calorimeters, and also 2 taggers, the low energy tagger inside the Chloe detector and the high energy tagger located at 11 meters from the interaction point, in order to measure the deviations of the leptons from the mean orbit of Daphne. Here I report a summary of the Chloe 2 data sample. In particular, during the Chloe experiment, we collected 2.5 inverse femtobarn of integrated luminosity on peak, with also an additional sample of 250 inverse picobarn of peak. Instead, during the Chloe 2 experiment, we acquired 5.5 inverse femtobarn for a total integrated luminosity of about 8 inverse femtobarn. That is the largest sample collected at a 5 meson mass with a collider. So let me report now the final results on the PCP inviolating process E-type plus pi minus decay. As you know, in the standard model, the branching ratio prediction of this process proceeds only via the CP violating in weak interaction with a branching ratio that is less than 10 to minus 27. Introducing a CP violating term in the strong interaction could enhance this limit to 10 to minus 17. Along also CP violation phases in the standing sector, the decay could generate with a branching ratio fraction of the order of 10 to minus 15. The observation of a large branching ratio means new source of CP violation with strong interaction. Up to now, the best limit has been published by Chloe in 2005 and also is reported in the picture, and also a recent limit has been published recently by the LCB collaboration with using a data set of 3.3 inverse femtobarn. But also a new search of the E-type plus pi minus decay has been studied with a larger sample of Chloe of 1.6 inverse femtobarn. In the plot, you can see the invariant mass distribution of pi plus pi minus, where the irreducible background has been evaluated with the eta band fit by using a third order polynomial function. Of course, it is reported with the red line. The black line, of course, are the data. And in blue, you can see the Monte Carlo simulated shape that was represented with the branching ratio, with the arbitrary branching ratio, just for visualization. Since non-evident peak is present in the data in the eta region, in the eta mass region, we extract an upper limit and we found the following branching ratio. We combined also these results of corresponding to the data of 1.7 inverse femtobarn with the previous Chloe result published, and we found that we have a branching ratio a factor 3 smaller than the previous one. If we consider the full Chloe-2 statistics, we expect to reach the following branching ratio. Now I will report about the status of data in pi0 gamma-gamma analysis. As you know, this decay is discussed in the framework of the chiral perturbation theory. This process is dominated by the 6th order the momentum expansion, and the problem is that there is an important discrepancy between the performed measurement up to now that I here reported. For this reason, a new Chloe analysis is in progress with a sample that is almost 4 times larger respect to the old Chloe preliminary results. And in particular, in the right part of the slide, you can see the process that we are studying, and in the down part, the preliminary results of the 4-photon invariant mass, where you can see with the black points the data, with the red line the Monte Carlo sum that include also the signal. In particular, in this new analysis, we implemented, in this new study, we implemented a multivariated analysis, BTT-based, to reject the big amount of events from the eta in 3.0 decay with loss of merged photons that is represented with the light blue histogram, and while with the dark blue are represented the other background channel with the green the signal. And with this multivariate analysis, we were able to reject, in this case, the 50% of the background event coming from the eta in 3.0. Another analysis ongoing is the B boson search. As you know, the light meson decays are very suitable for discovering new forces below the JV scale. A possible gauge boson is the B boson that couples mainly to work. It may be observed in rare relative decays of eta, eta prime, omega, and phi mesons as a pi gamma resonance. In particular, the process that is analyzed, that we are analyzing in Chloe is the phi in eta B with beta in pi 0 gamma. And we are using a sample of 1.7 inverse femtobarn. In the down plot, you can see the preliminary results of the invariant mass of the pi 0 gamma. Of course, in black are reported the data. In red, Monte Carlo sum, and in green and purple, the main background channel. At the end of the selection, we found for this analysis a detection signal efficiency of 12%. Another one physics goal of the Chloe 2 experiment is the precision measurement of the pi 0 width, which is considering a fundamental test of low energy QCD. The precision needed to test the QCD predictions can be achieved through the study of the pi0 production in the following process. And for this reason, we installed the ICHEP tagger at 11 meters from the interaction point to measure the deviation of the leptons from the main orbit of Daphne. The analysis strategy is the following. So to consider the it's in one HT station and 2 clusters in Chloe, originating from the same bunch crossing, what we call A plus sample, and evaluate also the uncorrelated HT Chloe time coincidence, what we call the A sample. Then we want to estimate the number of pi0 tagged events from gamma-gamma fusions from the difference between the A plus and A sample. But the problem is that the HET counting rate is dominated by low-angle radiative bubble scattering. The evaluation of the radiative cross-section is very useful to check the HET detector operational stability and also to validate the acceptance and efficiency of the detector by comparing the BBRAM simulation. In the left part, you can see the raw cross-section per scintillator, and in the closer plot, you can see the raw cross-section for the more stable scintillator. You can see that we are too peak in the distribution that are due to a decrease of the efficiency of the detector during the time. In the right part, instead, you can see the raw cross-section as a function of the time, and in the bottom part, you can see the luminosity pattern as a function time, where is compared the HET luminosity estimation and the Chloe luminosity measurement. And you can see in the picture a zoom just to see the agreement between the two evaluation. Of course, for the by zero search, only the scintillators starting from 11 to 28 are used, so only the more stable. Now I'm going to show the results on the gamma in pi0 search. Up to now, 1 inverse femtobarn of data has been analyzed. In particular, in the left plot, you can see the bidimensional fit of the gamma in various mass as a function of delta t, and in the right plot, you can see the output of the fit that shows 3.5 kilo-target events in the mass region, where the gamma in pi0 events are expected. As you can see, we have to improve the precision of our measurement. To this, we performed a new signal modeling using the outcome from the most updated resolution trigger threshold studies, because a multivariate analysis with an accurate signal modeling is crucial to improve the precision and eventually also to estimate the target events. Actually, the multivariate analysis is ongoing on the full reconstructed data sample that is about 2.5 inverse femtobarn. Concluding, the Chloe 2 experiments collected a data sample with an unprecedented statistics. The large data sample of light mesons available provided important results on the decay dynamics, together with the limits on new physics. The most stringent upper limit on the E-temper plus per minus decay has been presented, together with the preliminary results of the beam boson search, eta in pi0 gamma decay, and also the progresses on gamma in pi0 search. Thank you very much for the attention.
Thank you very much, Veronica. So let's see if there are questions. Please raise your hand if you have any questions. I don't see any, so thank you, Veronica, again.
Thank you.
And let's move to our next speaker, who is Runkyu Ma, who will be talking on light bearing spectroscopy at BESS3.
Okay. Good afternoon, everyone. My name is Runkyu Ma, and I will give a talk of light hadron spectroscopy at BESS3. And charmonium decay to light hadrons take place through cisibal annihilation, which is a gluon-rich process. And quantum number conservation in charmonium decays will make the analysis much easier with respect to these scattering experiments. And the background of high statistics data sample from E plus E minus production are very low. And BESS3 has the world's largest JSI and Psi prime data sample provides an ideal place for study light hadron spectroscopy. Okay, first is the study of scalar and tensor globules. Globule is formed by non-abelian gluon-gluon interaction. Study of globules is critical for understanding of confinement and the gluon field. And the latex QCD predicts the low-lying globules has ordinary quantum numbers. The most outstanding features of scalar meson is the overpopulation. The established scalar are more than the positions in the quark model. And this indicates that there are additional effective degrees of freedom beyond the QQ bar configuration. A widely accepted idea is mixing of global and nearby mesons. So which one has a more gluonic component? We need a systematic study for searching for outnumbering of conventional quark models states and abnormal properties. And with 1.3 billion JSI events, we performed amplitude analysis of JSI decays to gamma k short. The model dependent analysis is well consistent with model independent analysis. In the results of amplitude analysis, the branching fraction of F0 1710 is 1 order of magnitude than that of F0 15100. Similar feature of branching fraction is also observed in the amplitude analysis of JSI decays to gamma eta eta. And the tensor contribution about 2 GeV is dominantly F2 2340. So for the scalar global candidates, from latex QCD prediction, the mass of scalar global is 1.5 to 1.7 GeV, and the mass of F0 1710 is consistent with latex QCD prediction of scalar global. And with new measurements from batch 3, the F0 1710 has been founded in many channels, and the known branching fraction of JSI decays to gamma F0 1710 is up to 1.7 times 10 to the minus 3, which is already comparable with prediction of global, the scalar global. And in contrast, the corresponding branching fraction of F0 15100 is much smaller than that of F0 1710. This indicates that F0 1710 largely overlapped with scalar global. And for the tensor global candidates, from latex QCD predictions, the mass of tensor global is 2.3 to 2.4 GeV. With the new measurements from batch 3, the known branching fraction of JSI decays to gamma F2 2340 is still much smaller than that of prediction of tensor global. So we need more measurements. And next, we'll move to the study of pseudo-meson spectroscopy. The X1835 was observed by batch 2 in JSI decays to gamma eta prime pi pi, confirmed by batch 3 using the same decay channel with more JSI data. And anomalous strong PP bar threshold enhancement structure was observed in the JSI decays to gamma PP bar by batch 2 and confirmed by batch 3 and Clio. The X8035 and XP bar have been extensively studied in many channels. The GPC of X8035 and the XP bar is 0 minus plus. And with higher statistics, a fine line shape study of X8035 shows an anomaly at P bar threshold. This may indicate P bar molecular states or bound states. And with 1.3 billion JSI events, we had observed X8035 in with 6.3 sigma in JSI decays to gamma gamma phi. Meanwhile, we also observed eta 1475 with 30.5 sigma. Since X decays to gamma V with V equals to rho or omega do not change the flavor structure of X. So the final state vector meson V act as a flavor filter. So X8035 and eta 1475 has sizable SS bar component. And the angular distribution of X8035 and eta 1475 both favor GPC equal to 0 minus plus. And with 1.3 billion GSI events, we also trying to search X1835 in GSI case to omega eta prime pi pi. No obvious signal of X1835 is found, and the upper limits on the branching fraction at 90% confidence level is set. So for the pseudo-scalar global 0 minus plus, besides X1835, X2120 and X2370 and eta C is also observed in GSI case to gamma eta prime pi pi. From the lattice QCD prediction, mass of ground states of pseudo-scalar global is 2.3 to 2.6 GeV. The small number of expected pseudo-scalars in the quark model provides a clean and promising environment for the search of globals. However, experimentally, very little is known about the 2 GeV. So the mass of X2370 is close to the prediction of pseudo-scalar global. Maybe it's a global candidate. And we assuming the pseudo-scalar global at 2.37 GeV decays to eta prime pi pi, a sizable decay with to eta prime kk is predicted. And in the study of GSI decays to gamma eta prime kk, we had observed X2370 with 8.3 sigma, and the mass and width are well consistent with X2370 observed in GSI decays to gamma eta prime pi pi. So in the future, amplitude analysis is needed to identify the GPC of X2370, and we need to find another decay channel. And meanwhile, no obvious signal of X2120 is found. The significance is 2.2 sigma. So next, we will move to strontium spectroscopy. Strontium mesons form the intermediate region between light and heavy. And one of the interesting topic is Phi 1680, a nature which is a nature candidate for the radial excitation of Phi 1020. So Phi 1680 is well established in the E plus E minus production. But the measured mass and width is very different with the result of photon production, which was reported as new resonance X7050 by Focus. To better understand the discrepancy, we performed an amplitude analysis of psi prime decays to k plus k minus eta. The result is shown in this table. Both Phi 1680 and X7050 were found at the same time. This may explain the previous discrepancy in Phi 1680, and Phi 2170 or Rho 2150 is also observed. The Phi 2170 was observed by Babar and confirmed by Bell and Bess3. At this analysis, the atom spin is undetermined, so we need a combined analysis with other channel to pin down the atom spin. And with 225 million GSI events, the amplitude analysis of GSI decays to k plus k minus pi 0 have been performed. And we got two solutions. Solution 1 is are using PDG states only, and the solution 2 are using PDG states plus a slow changing background in the GP equals to 3 minus k pi partial wave. In both cases, there is a set of reliable identified contributions. The result is shown in this table. And first, the K-star 892 and the K2 1430 measured with high precision, and the K2 9080 and the K4 2045 are observed for the first time in GSI decays. Mass of K2 1980 agrees with the linear ridge trajectory of radial excitation. And most importantly, 2 GPC equals to 1 minus states decaying to k plus k minus are observed. The first one is around 1650 MeV. It may be isovector states or isoscalar states. The second one is around 2050 MeV. It may be Rho 2150 or the states observed in this article. And next, by replacing the CC bar pair in the CC structure with an SS bar, it is possible to consider an analogous ZS structure. And CC 39100 was observed in the pi G final states in batch 3 and Bell. Mass are close to the D bar threshold. So according to this channel, 52170 could be a strange analog Y4260, which may provide a place to search for CS states around the K star K threshold. And there is a theoretical prediction that a sharp peak structure CS1 close to the K star K threshold and broad enhancement CS2 around the K star threshold exists in the 5 pi invariant mass spectrum of the 52170 decays to 51020 pi process. So by setting the center of mass energy to 2.125 GeV, we performed an amplitude analysis of E plus E minus decays to 5 pi pi, trying to search CS. And the data can be well described by this 5 process, and no sign of CS is seen. The upper limits on the branching fraction at a 90% confidence level are determined for different mass and weights and the GP hypothesis. So to summarize, battery collected 10 billion GSI events in last year and will continue to run for about 10 more years. Data with unprecedented statistical accuracy provides great opportunities to map out light meson spectroscopy and study QCD exotics. That's all. Thank you for your attention.
Thank you very much, Ronki. We are back on time and we still have a few minutes for questions, if there are any. Please go ahead. Okay, I don't think any questions. So let's thank our speaker again.
Okay, thank you.
Thank you, and then we'll move to Ralph Seidel. Can you please, Ralph, try to share your screen?
Yes, and I think it should actually be working now.
Yes, just go full screen and I think we're set to go. Yeah, go ahead.
I think you should see it now. Okay, so we changed gears a little bit. We're coming now to fragmentation function measurements, and I'm reporting about those which are coming from the Bell experiment. So as you are probably aware of, fragmentation functions describe the fragmentation of colored partons into color neutral final state hadrons. And they are also non-perturbative, so we have to actually extract them experimentally and cannot calculate them from first principles. However, they actually appear in many processes and are universal, so we can use them actually also, in addition to trying to understand them, to actually get input on the study of the nucleon structure or the structure of QCD in itself. So therefore, for example, if you look at semi-inclusive DRS, you see actually fragmentation functions appearing with distribution functions together in nucleon-nucleon collisions. If you have a hadronic final state, those appear as well. And also in your plus and minus annihilation, you can actually measure them. That process in particular is very important because here you have no hadrons in the initial state, and therefore you can cleanly actually extract the fragmentation functions that are entering. So because of that, we have been actually doing this. So there's a large program of different measurements which we have been doing actually at Bell and also at other E plus E minus accelerators to extract fragmentation functions. So here you see actually a list of the various different fragmentation functions which have been extracted over the years, so unpolarized ones, polarized ones, single and dihadron fragmentation functions, as well as then explicit transverse momentum dependent ones. So basically, Bell has contributed to almost all of them in the recent years. And we have quite a large number of measurements available here that can actually contribute not only to the understanding of the fragmentation functions itself, but then also of the spin and nucleon structure in itself. Today, I will be only concentrating on the unpolarized parts here, where we have a few very recent publications that I want to mention today. These measurements are all have been taking place at the Bell detector at KEC-B in Japan. And as you are probably familiar with, it's an asymmetric E+E- collider, mostly sitting actually at the ε4s resonance, but also slightly below that. And in either case, actually, your dominant contributions are actually QQ bar production, which then can be used actually to the study of fragmentation functions. And in total, we have actually extracted more than an inverse autobahn of data actually from E+E-. So let's get started. This is already an older result, which we have published in 2015, which is the identified pion, kaon, and proton fragmentation functions as a function of the fractional energy C, which is basically just naively the fraction of the hadron relative to the outgoing parton from which it fragmented. Those have been extracted in actually quite some precise binning, and with everywhere being actually systematics dominated. Since then, we have actually updated them. That is actually quite recently happened. We have actually updated them by using actually a better ISR correction. So for the initial state photon radiation, that is more directly applicable actually to the global fitters, such that they can use the data more easily. And also in order for them to actually improve their sensitivity, we also actually separated the correlated and the uncorrelated uncertainties for the different measurements, such that the overall impact of this data set will be larger than it was before. You can see also on this slide actually several lines compared to the data, which show various tunes actually from Pythia for the fragmentation. We see that the Pythia default setting generally describes pions and kaons very well, but essentially for protons, which are of course baryons, the fragmentation seems to be not really so well described, and essentially none of the tunes we tested can actually describe the proton data over all the range. I will be coming back to that the baryons are actually special in that case a little bit later. We have also not only extracted these unpolarized single hadron cross-sections as a function of the fractional energy, but also actually explicitly studied the fractional energy and transverse momentum dependence. So you can see here that we've been using actually the event variable thrust as the reference axis, which of course approximates the QQ bar axis, and then calculated the transverse momentum of a detected hadron relative to this axis. After having done that, we extracted here on this slide the width of the Gaussian transverse momentum distribution, and we can describe this reasonably well by a Gaussian. We see that for pions and kaons, the behavior is very similar, and within their systematic uncertainties, they are actually consistent with each other. Maybe the pions are a little bit more narrow. But you see that the width of the transverse momentum distribution increases actually up to medium fractional energies before it then drops down as you're getting more and more constrained and cannot go actually too far away from the nominal parton direction. Also here you see actually that the protons behave quite differently. So their width is generally much smaller than that of pions and kaons. And one of the possible reasons is that, of course, in the fragmentation process to produce a baryon, you have to actually pull out a diquark pair out of the vacuum. And therefore, it seems that you're not allowed to actually deviate too far from the initial parton axis. And therefore, the width of those seems to be narrower. Then we can go actually from single to dihedron fragmentation functions. And there you can actually distinguish two different types of dihedron fragmentation. One, which is really a typical dihedron fragmentation, where you detect two hadrons in the final state relatively close to each other, such that it's most likely that they're coming actually from the same initial parton. Or you could look at two hadrons in the final state, which are far away from each other, so basically roughly back to each other. And then these two actually comprise two single hadron fragmentation functions. And we've been actually also extracting those previously, and we have been now updating those measurements, not only with more precise treatments like before, but also actually including two different fractional energy definitions in addition. So the nominal fractional energy definitions in E plus E minus are just the energy of the hadron divided by half of the center of mass energy. However, there exist actually two definitions which are particularly suitable for dihedron cases, as they concentrate mostly on close to back-to-back hadron pairs. The oldest definition is actually from Altarelli already, where the first fractional energy is the same, but the second fractional energy has now actually a dot product of the 4 vector, and therefore of the two hadrons, and therefore it only has a large support when the two hadrons are actually nearly back-to-back. And because of that, this definition is actually very suitable also to next to leading order fragmentation analysis of dihedron measurements in E plus E minus. The other definition is very new. It's coming from Piet Mulders and Charlotte van Hulst, and it uses a similar idea as the one from Altarelli, but also takes into account explicitly the masses, and therefore essentially is also sensitive to the transverse momentum which is generated relative to each other between the two hadron pairs. So first of all, before we get there, from the previous results, I want to show you here for diagonal fractional energies for the nominal Z definitions, the contributions of dihedrons within the same hemisphere in gray and within opposite hemispheres in the shaded region. And the interpretation that those in the same hemisphere are coming essentially from the same parton are actually consistent with the fact that the fractional energies drop out to 0 at around 0.5, whereas those in opposite hemispheres coming from a quark and an antiquark separately reach out to actually fractional energies of close to 1, and therefore are coming from different partons in this case. So using that, we can then actually look at the different updated fragmentation functions. So here you can see the various final states for pions, same and opposite charge, pion-kaon combinations and kaon-kaon combinations as a function of the fractional energies of one hadron in each panel, and then actually on the x-axis, the fractional energy of the second panel. And this is actually showing you the nominal definitions. And you see those are actually, as you would expect, that pions are generally dominating, but because at the Bell energies also you have quite a substantial amount of charm fragmenting, actually the pion-kaon pairs become actually quite similar intermediately as well. If we look at the differences between opposite hemispheres and any hemisphere, you see that at high Z, they are changing not at all because they can only come from opposite hemispheres, but you get actually some additions at at smaller C values. If you then compare actually how these different definitions look like, so now only showing actually the pion pairs for unlike sign and like sign pairs for the 3 different definitions. On a logarithmic scale, you can hardly see actually the differences between them for the 3 definitions. However, if you look at the ratios to the default definitions, you see that there are quite sizable differences. As I mentioned, the 2 new definitions concentrate mostly on the hadrons to be back-to-back. And that's what you can see, that at very high Z, generally you actually reach unity. So there the definitions make no large difference. Whereas at lower Z, they're actually substantially smaller by, yeah, at least 20% or more for the newer definitions. In addition to that, the Mulders-van Hulst definitions are even smaller still, because they also have to accommodate the additional transverse momentum in them. And that's why you see that they're also not exactly matching the other definitions at high Z either, since there's still a remainder of transverse momentum available there as well. If you go to the any hemisphere, then you get this additional contribution at lower Z from the same sign hadrons. And those, of course, do not appear basically in the newer definitions. Therefore, you see that at low Z, the distributions are much more suppressed here, as you do not have these contributions at sizable Z values. And above Z's of 0.6 or 7 at higher Z, you see that they are actually then again consistent with each other. Either you look at one hemisphere, any hemisphere, or the opposite hemispheres. And that brings me actually to my summary. So as I try to show you that fragmentation functions can provide a very important input for the understanding of QCD, as well as that of the understanding of the nucleon structure. And the E plus E minus experiments have really provided a large amount of data, in particular the Bell experiment, for nearly all of the relevant fragmentation-related measurements. So I showed you today the single and dihadron cross-sections, but we also have the polarized column interference fragmentation measurements, transverse momentum dependence I showed you also. And essentially all of them will be absolutely essential for any of the semi-inclusive EAC measurements that are going to come in the next decade. Thank you.
Thank you very much, Ralph. There is a question by David. Go ahead.
Thank you. Can you hear me?
Yes.
I can hear you.
Very good. Nice data, Ralph, as usual. Can you go back to slide 8? I have always a question, and I don't think I understand it. When you take the ratios of the fragmentation functions to different data, Aleph, Leb, Hermes, what do you mean by that? Yes.
Those are, yeah, I didn't have time to explain this today. Those are not data, those are actually Monte Carlo tunes in Pythia that are actually coming from these experiments. So they're all actually Pythia simulations, and I'm comparing them at, of course, the Bell center of mass energy, and compare them actually to our data measurements. So that's why here you see that they're all the Monte Carlo ratios to the data actually.
Okay, understood. Do you have, do you know if there is any comparison to the refitted fragmentation functions from the Argentina team? I think they did the latest global fits. How do they compare, in particular for the protons? This discrepancy has been solved or not yet?
Actually, so for the pions and kaons, our data is actually part of the DSS fits. So that has been actually included already in our data. Of course, the older ones, so the significance with the newer data due to the improved systematics will probably increase a little bit. I'm not aware of them actually studying protons yet. I think some of the older global fits tried this, but I think there you don't have quite as much precision data, and I think certainly not any very new fits, I believe.
And one last question: do you have the same fragmentation functions but focusing on the low Z region? So Heimbach plateau region. Do you provide this for the inclusive charge hadrons? Do you have those, or you only have the?
No. So the low C, that's, yeah, I know that some people are very interested in this, but so from the standpoint of the nucleon structure, those are essentially not relevant. And so for us, we are not really using them. In addition to that, you also have to be very careful because at the B energies, the B factory energies, you of course get into issues already with the masses of the hadrons. So you see, for example, for the protons, we cannot go lower than 0.2 in fractional energy. For the kaons, we can go somewhat lower, but this is also stretching it basically. And only the pions, you could actually go down to values which were much lower than 0.1. But for example, I know that DSS excludes these ranges anyway in their fits.
Yes, but there are different approaches that use the lower Z data to do different fits, as you know. Thank you.
Other questions for Ralph? Okay, if not, thank you, Ralph, again, and we'll move to our last presentation of the session by Giacomo Volpe. Giacomo?
Yes, I'm here. So I start sharing. Do you hear me?
We can hear you, yes.
Okay, I start share my... Is it Zoom? Okay, I think that for share I have to exit and enter again. So if you wait a bit.
You just need to click on the green button at the bottom.
Yes, but it needs, I don't know why I need to, you know, for my computer is asking to give permission. And to do this, I have to exit a few seconds.
We can see already the screen.
Okay, so it's fine. Do you see my slide?
Yes, go ahead.
Okay, so fine. Let me also open the cam, if I can. Okay, so I'm Giacomo Volpe from the Bari University. I will talk about the study of hadronization through the measurement of light flavor particle production, different colliding system with ALICE. So where is the but I don't see the slide. I don't see my. Okay, so ALICE is designed to study the physics of strongly interacting matter under extremely high energy, temperature and density condition to investigate the property of work on plasma. So to do this, ALICE has collected proton-proton collision that works as high energy QCD reference, but also proton-neutron collision to test the initial state, including a matter effect. And then, of course, nucleon-neutron collision, where gluon-gluon plasma is supposed to form. So ALICE measured the yield of pion, kaons, protons, strange and multi-strange particle in a wide momentum range in several colliding systems as a function of even multiplicity, giving the possibility to investigate the hadronization mechanism. Let's start from the hadron yield measurement. So ALICE measured the hadron yield of different particles, and the hadron yield can be described by the statistical hadronization model. So particles built from ideal hadron resonance gas in thermal and chemical equilibrium at the chemical result. So the measurements are compared with the prediction of the model, and production of most of light flavor hadrons in lead-lead collision are described by the model as we can see here, using a single chemical result temperature equal to 153 MeV. Anyway, we can observe a deviation for K0 resonance because there are maybe due to the scattering, the late hadronic phase, and this has been excluded from the fit. And there's also attention for protons and multi-strange hadrons. This probably due to an incomplete thermal spectrum and then to the baryon annihilation in the hadronic phase. So then this decrease a bit the antiprotons and proton yield, and then to the interacting hadron gas at flavor-dependent result. Important information can be also retrieved from the PT differential ratio. In central PP collision has been observed an enhancement of the baryon-Vermeerson ratio at intermediate PT. This is explained by the hydrodynamic model. So the medium forming the collision undergo a radial flow, and of course particles with heavier mass undergo have an higher momentum. So this explains the peak, but also recombination model can explain the observation. So we can have a mass ordering due to the hydrodynamic effect or particle time ordering due to the recombination. If we look to the proton over phi ratio, where we have one baryon and a meson, but with the same mass, we observe a flat ratio. So the effect should be connected to the mass, also explained by hydrodynamic. Anyway, also model with the recombination can explain the behavior of the proton over phi ratio. So this is lead collision, but what is the situation in also in proton-proton and proton-lead collision and multiplicity? Has been observed qualitatively similar feature for both particle production in the different colliding system, so also in proton-proton and proton-lead collision. So in a qualitatively similar way, we observe a depletion at low PT and an enhancement at intermediate PT. And this, in lead collision, as I said, is explained by radial flow, essentially. We observe also a similar progression of the yield for the proton over pyroration across different systems. So if we observe then the ratio, we see that there is a progression if we go from proton-proton to lead collision with the multiplicity. So this effect is explained as collectivity effect in lead collision, and this is, if it is true also in proton-proton and proton-lead collision, this should not be observed in jet. We have measured also the baryon-Vermeerson ratio versus PT in jet and out jet, and we see that the enhancement is due only when we study the bulk of particle. If we study only the jet production, then the ratio is flat. So this is connected to the evolution of the underlying event. If we compare then the proton over pi ratio, so baryon over meson ratio, to models, so this is proton-proton collision, where in principle collective effect should be there, we see that, for instance, Pythia with
Hello, can you hear me?
Yes, I think we lost our speaker.
Yeah, maybe we can wait a bit.
I was wondering if it was my problem, but looks like it's his. Let's wait a few minutes. Well, he's our last speaker, so we cannot move to anybody else. Okay, it looks like Giacomo is having some issues. So I just remind everybody that we have also a poster session starting at 1:30 in a few minutes. So maybe if we'll wait still a couple of minutes for Giacomo, but maybe if there is still issues, he can make his presentation at the end of the poster session or something like that.
I think we have a question or comment.
Yes, Rainer, you want to say something?
Yeah, I would like to ask in this round, it's not physics related. I'm losing the sound every few minutes here in this Zoom for the last, starting about 2 hours ago. So I was just wondering whether that's my local problem or whether anybody else experiences the same. Then it might be a Zoom problem.
It's working fine with me. I don't know about the other people, but
No,
I
for
haven't
me,
heard.
I don't see this problem. Maybe I'll try to restart Zoom, just in case.
So I think, I don't know what Antonio thinks. Maybe we can try to schedule Giacomo's talk at the end of the poster session at 2 p.m.
So maybe I'll Yeah, so you said that the secretary is already trying to get in contact with him. So maybe I mean, if we have some feedback by the end of the poster session, then it's fine to have his talk at the end. I'll be around, so
okay.
I could talk to him. If he reconnects, I could propose this to him at the end of the poster session.
Yeah. So okay, so maybe we can stop here the session. Sorry about this little issue. Let me thank all the speakers again. So we can have a few minutes break, and there is the posters. Oh, here
You hear
it
me?
is. So we can hear you. Where?
Yeah, when you lost me, I didn't realize.
Well, you were about slide 7 or 8.
Okay, I'm sorry. I don't know what. Maybe there was a problem with the connection. So I could start from.
So if you pull up your slides again, I can tell you exactly which one was it. I think
Okay,
it was
yes, let me
number
check.
8. I think it was, maybe you can start from slide 6.
From here.
I think it was around slide 7 or 8, but maybe you can. Yeah.
Okay, yes. So I'm really sorry. I don't know what's going on. So let me. Okay, so I was talking about the PT differential ratio and lead collision. This by we observe an enhancement of baryon over meson at intermediate PT. And let's see what happened also in proton-proton and proton-lead collision. So we observe a qualitative similar feature for good particle production in PMP proton-lead collision. So in a qualitatively similar way, we observe a depletion at low PT and an enhancement at intermediate PT. And as I said, in lead collision, this is explained by radial flow. We observe also also a similar progression with the multiplicity is observed at fixed PD. So if we then consider the ratio, the integrated ratio at low PT, intermediate PT, APT, and we measure this as a function of multiplicity, we observe a progression, okay, for the proton over pion ratio, so baryon over pion ratio across the different system. So the enhancement, if due to the underlying event evolution, should not be present in the jet. We also measured the jet, the ratio in jet and out jet. So in out jet we can see the enhancement, but as I show here, in jet the ratio is flat. So this is a stronger indication that the behavior is due to the evolution of the underlying event. If we compare the proton over pion ratio, in general the baryon over meson ratio and PP collision with the Monte Carlo generator, we can see that PTA with color recognition describe quite well the trend. So in PP collision, radial flow can be mimicked by the QCD effect. Let's look now to the particle composition of the system to investigate if also shows similarity in the chemical particle composition. So for this, we check what happened on the strangeness sector. So strangeness enhancement that, as you know, has been observed in lead collision, but we have measured also the strangeness production in proton-proton and proton-lead collision as a function of multiplicity. So I show here the PT integrated yield ratio to pion versus multiplicity. The integrated particle ratio show an increasing trend for low multiplicity PP collision to central lead collision for stage hadrons. Comparing this with the Monte Carlo generator, we can say that the radial flow can be mimicked without hadron collectivity, but strangeness enhancement cannot. So further development are needed to obtain a complete microscopic understanding of strangeness production. So in PP collision, strange particle ratio to pion increase, as I show. But this is an enhancement, is due to mass, to baryon, meson, nature of particle, or strange content. So let's check what happens for the proton over pion and lambda over kaon ratio, where the only effect could be due to baryon, meson, or mass, because there is no a net strangeness difference. The ratio are flat. If then we check to the strangeness content doing the double ratio, so the integrated ratio of a pion in pp, proton level and collision as a function of multiplicity normalized to the ratio in minimum bias proton-proton collision, we can see that for protons, this ratio is consistent with unity up to the highest multiplicity. Proton is not a strange particle. Hyperon production increase for low to high multiplicity in pp and proton-level collision. So the larger the valence strange quark content, the steeper is the slope. So the effect is due to strangeness. Now we can ask how is the same enhancement present at different energy? So it is collision energy dependent or multiplicity driven. Alice has measured the strange hadron yield as a function of multiplicity in proton-proton collision at different collision energies, so 5, 7, and 13 TeV. So as we can see here, the trend is the same for the three energies. So it is collision energy independent and similar multiplicity. Before to go to my conclusion, let me talk about the special case of the phi meson. Phi meson is a long-lived resonance that contains two strange quarks, or strange and anti-strange. If we compare this to K and Xi particle in the ratio that I show here, so phi over kaon and Xi over phi ratio, the two ratios are both finely constant. Xi over phi ratio decreases with the decrease in multiplicity for the lowest multiplicity collision. So it behaves as if it had between 1 and 2 unity of strangeness. The multiplicity evolution is not consistent with simple description of canonical subtraction, but is qualitatively described by the Dipsy model that takes into account rope hadronization effect. At this regard, I suggest you to give a look to the Ganotti talk on hadronic resonance production measured by Alice at LAC. So let's come to my conclusion. As I show, Alice has performed a comprehensive study of pion, kaons, proton, strange and multi-strange particle production in different collision energy that are relevant to investigate hadronization mechanism in the different colliding system. The production of most light flavor hadrons, leather collision at 5 dV, is described by the statistical hadronization model with a single chemical freeze-out temperature. Yield and barrier over meson ratio evolve smoothly with multiplicity, and this is connected to collectivity effect, so hydrodynamic flow, radial flow. It is not observed in jets, indeed. Enhancement of strangeness production observed from low to high multiplicity PP and proton dependent at different collision energy is poorly described by common used Monte Carlo generator. And measurement at different energy as a function of multiplicity seems to indicate that the hadrochemistry is driven by event activity, so multiplicity, and not collision energy. Thank you.
Thank you very much, Giacomo. Other questions? I don't see any raised hands. So thank you very much again, Giacomo.
Okay, thank you. I'm sorry again for the inconvenience.
That's all right. So that concludes our session. Thank you again, all the speakers. And as I was just saying before, we have a poster session started right now that will be chaired by Antonio. Thank you.
Thanks. Bye.
Bye.
Okay, so actually, Martin will